the discovery of an alien civilization would be the absolute ultimate Nobel Prize. Perhaps the most likely civilization we'll detect is one who's the most unsustainable, because that's going to be the loudest. Burning all of the fuel that it has on its planet, is in the process of nuclear annihilation, and that kind of nuclear conflict would probably produce the loudest signature we could hope to detect.
I'm smiling, like almost giddy, just because I'm thinking about how fun it must be as an astronomer or astrophysicist to write these very rigorous scientific papers about how you would detect like space mining aliens.
My personal hunch is that we are more likely to make contact with a civilization who is in a very desperate state. There's no real incentive to say hi to anybody, except if you're on your deathbed. And if you're on your deathbed, you need help. Right? You're a civilization that you know you're about to hit your end. There's no risk in communicating at that point because you're going to die anyway.
At Columbia, you run Cool Worlds Lab, which focuses on exoplanet research. But then you also run the Cool Worlds Lab YouTube channel, which goes quite deep on questions related to aliens, the search for intelligent life. And what this makes me wonder is whether you started out with an interest in aliens and that brought you to astronomy, or whether studying astronomy came first and then that brought you to these other questions.
Yeah. When I was younger, I was always interested in space. I think, watching science fiction, Star Trek, I grew up in. Anyone who watches my channel knows that I have a lot of Star Trek Next Generation clips. I remember running home from school to watch those episodes and really being inspired by the futuristic engineering that was involved in this dream of a utopian civilization for humanity. So that really inspired me about what the future could be. And it seemed like humanity's future would be out in space, watching those shows and reading various science fiction novels. So I got inspired by that, and I always thought I would study astronomy. And then when I was at high school, I started to get more interested in physics. And one of my physics teachers, Mr. Fox, he's a really dear friend of mine after leaving school, he used to sneak away and kind of give me these physics books to read on the side, books that were way too advanced for most of the students, but he'd be like, I think you can handle this. So I'd read those books on the side, and I started to have this kind of transformation. It's almost like an awakening when you first start reading these books about quantum physics and particle physics. And you suddenly realize that the world is very different to that which you perceive. And there's all of these trillions of neutrinos blasting through your head every second. And you think, you stare at your hand and you think about the constituent atoms and electrons and protons and quarks that are all going on inside there. And it really just kind of blows your mind. And for a few years, I was convinced I would study, pure fundamental physics. I went to college at Cambridge University, and that's what I signed on to do. The degree there is called Natural Sciences, which I really love. It's kind of more like the US system where it's very broad. So you start out studying chemistry, mathematics, geology, physics, and each year you drop one subject and sort of narrow down. But I always thought it's physics that I'm going to do. And I did probably only a few classes in astronomy during my degree because it was primarily a physics degree. But I really started to become inspired by astronomy during that time. The discoveries of exoplanets were happening. We had one class, I remember, from a professor who has said, by the way, there's this thing called exoplanets that are happening, and we've discovered a handful of exoplanets now, but it's not really a big deal. And I was like, hold on. We've just started discovering planets outside the solar system? This seems like a very big deal to me. And of course, as a young person, you want to find something that's like a growth area, right? So if you look at particle physics, it felt to me, right or wrong, that was an area that had reached maturity, that it was going to be very difficult now to make further progress. The LHC was a $13 billion machine, and the number of authors and the size of the teams were gigantic. You're one of thousands of cogs in the machine. And I didn't really like that. I wanted to be, I'd rather be a big fish in a small pond than in this giant collaboration. So I drew towards exoplanets because when you look at that, there were pioneers. There were, just one person or two people like Michel Mayor and Didier Queloz who won the Nobel Prize for the first exoplanet. The discovery was in 1995. I think the Nobel Prize was 2017. It was just the two of them, and they were radicals, they were mavericks, and they were laughed at by their colleagues. And that was really appealing, to the idea that there was these people breaking out, doing something new. So I think, I was inspired by those stories and thought that's where the growth area is. And of course, to come back to your question about aliens, exoplanets is a story ultimately that has to end with a question of aliens for me. That is the end point of this journey we're on. Now, a lot of exoplanet astronomers shy away from that, and they like to pretend it's a pure science and we're only interested in the nature of these planets and that's it. And I find that really strange because, what are we doing? If we're characterizing these planets, we want to know if they have oceans, we want to know if they have atmospheres, we want to know if they have continents, and you keep going a step further. Surely the end point of that is there someone living on that thing? And could we potentially communicate with them or interact with them? So for me, that's always been the natural end point. And I've never shied away from that. In my career, I've participated in both of those activities.
The first thing that comes to mind is it's an interesting point that you chose to go into exoplanet research to be a big fish in a small pond, because we do know that, the standard model of particle physics, it hasn't been improved upon in quite some time, but we haven't found a planet that has life yet, as far as we know. So there's so much work to be done there. And another point that's interesting that I wanted to ask a bit more about before we talk about futuristic engineering and alien civilizations is this idea that a lot of other exoplanetary researchers shy away from talk of aliens. And I've had Avi Loeb on the show, and he's very interested in these questions, but I've also heard other physicists and astrophysicists behind his back talk about how, I wish he wouldn't do this. It's so bad for the field. And what this makes me wonder is, I'm not asking for a commentary on Avi Loeb, but how you think a scientist such as yourself should go about the research into aliens and possible intelligent life in a way that's scientifically responsible.
Yeah, that's a great question because it is a topic which is very seductive and easy to get drawn into the sensationalism of it all, because it's the ultimate scientific discovery, right? So even I think any question in science, trying to understand the origin of the universe and the nature of dark energy, dark matter, all of those are crucial, massive questions in science, but at least in my opinion, I think the discovery of an alien civilization would be the absolute ultimate, Nobel Prize, like the Nobel Prize cubed. That would be what that would be.
The question whether or not we're alone is just one of the biggest questions. So it's crazy to me that it should be off the table, as it's just a matter of how to go about it.
I think the reason why a lot of scientists are cautious about it, and I don't want to speak as if there's a uniform position on this, because of course there's diversity of views amongst my colleagues. There are certainly many colleagues who shy away from the question, as I initially said. I think that's true. And there are many, like Avi, who embrace it wholeheartedly. But I think the reason why some folks have a resistance to it is because of the number of burns we've had in the past.
Burns?
So there have been numerous false claims of alien life. And you can go back all the way back to sort of the 19th century. You had Percival Lowell, who was a very famous astronomer. He was first an industrialist, almost like a sort of Elon Musk type character of his time. And then he got fascinated by space and astronomy. He actually built his own observatory in Arizona. It's called the Lowell Observatory. Still runs today, and lots of tourists go there. And if you're in Arizona, you should go visit it. It's beautiful. And he really had a passion for looking for alien life on Mars. And Mars was obviously the nearest world that we were starting to get these wonderful images from refracting telescopes at the time. So he noticed a couple of things. He noticed there seemed to be an atmosphere. He could kind of see this almost silhouette around the planet. So he thought, okay, it's got an atmosphere. It's about the same size of the Earth, more or less. It's about half the size, but within the right ballpark. He noticed it had polar ice caps, which is true. So it has water, therefore, not liquid water, but it has a source of H2O. And so he started to think that this really could be a place where life could exist. And he became convinced of it. And I did a video about it on my channel a while back, and there was a quote, I'm probably going to misquote this a little bit, but he said something like, the probability that Mars has life is as certain as gravitation, the laws of gravitation. So he was just, even before he had any evidence, he was so convinced that life was an inevitable byproduct of natural processes that Mars has to have life on it. In fact, has to have a civilization on it. And that's dangerous because then you've got experimenter's bias. When you think you know the answer to an experiment before you've done the experiment, you're only going to sort of have this confirmation cycle where you start to see what you want to see. And indeed, that's what happened. He saw these canal systems. He thought there were canal systems on Mars and started to write about that. And for a good decade, a lot of the world thought that there was a Martian civilization that built canals. And of course, he was seeing a reflection of humanity's own technology development because, of course, canal systems were being built across the US at the time. So he thought of this as the inevitable thing. And so if you look at modern astronomers, they often say, okay, solar panels, we're building solar panels everywhere. So other planets will surely be covered with solar panels. And I just think we have to be careful with that because we've seen that with Lowell, that when you take a reflection of what we're doing now and project it onto other planets, it's kind of laughable. The idea of a canal civilization just seems silly now. And I think whatever technology we have now will similarly be kind of laughable in the future. So I think this is just one example, but there's been Martian meteorites. There's the Alan Hills meteorite, and Bill Clinton in the 90s, I think it was like 1992 or 3, stood on the White House lawn and presented evidence of alien life on Mars again. That evidence ended up being highly challenged and criticized by the community and is not really considered legitimate anymore. You have Venusian phosphine just in the last few years. That was a big news story that was thought to be life. Of course, there's Oumuamua that Avi Loeb's been writing about, claiming that this interstellar asteroid could be a spaceship. And, that, I guess we haven't got convincing evidence against that, but by and large, the community do not favor that hypothesis. So there have been many, many, many instances of someone crying wolf, I would say, at this point. And so the community is nervous about it because you can get laughed at. And, that has happened to many of these astronomers that I've mentioned. They've been kind of ridiculed for that activity. And that's tragic, I think, when that happens, because SETI, the Search for Extraterrestrial Intelligence, SETI, has for a long time had this giggle factor element that you say to someone, I'm looking for alien life with radio telescopes or whatever method you're using, and astronomers, scientists will kind of laugh at you and say, oh, that's kind of ridiculous, isn't that cute? Why don't you do some real science? Why don't you study cosmology or something? And that's really dangerous because it turns great minds, great young thinkers away from this really important intellectual activity. So there has been this tendency, this dangerous tendency to laugh at SETI, and SETI has been working really hard over the last 5 decades, 6 decades to build a very credible research program. And I think now it has lost that giggle factor largely, which is great. But it's always easy to slip back into it, that you start making claims that X, Y, or Z could be aliens. And that's easy, right? Because aliens is infinitely flexible. It can explain everything. Any new observation I present to you, it's got off the gaps. I can always just say, aliens did it. It has unbounded
Can you give me an example
capability.
of what you mean by this?
Let's say a good example would be pulsars, actually. So when pulsars were first detected, these are the collapsed remnants of massive stars. Very massive stars, when they end their life, the sun will not do this, it's not massive enough, but they can collapse either into a black hole or a neutron star. A neutron star is sort of not quite massive enough to go all the way to a black hole. A neutron star is basically a giant atomic nucleus, essentially. It's just you've collapsed all the way down so that you've overwhelmed electron degeneracy pressure, and you've just really got something bound by the strong force, essentially, in gravitation. So at this point, these stars can rotate and then have very strong magnetic fields, and it's like a lighthouse of these radio waves passing across the sky. And so when these were first detected by Jocelyn Bell in the late 60s, I think it was, they were actually first called LGM1, Little Green Man 1. And that was a little bit tongue-in-cheek, but it did precisely match the kind of signature people anticipated an alien civilization might produce, which would be a strictly periodic, rapid, high-powered radio signal directed towards the Earth. And that's what this signal looked like. And it was very difficult to imagine what else it could be at the time except for aliens, because there wasn't a real theory of pulsars at the time. So that was an example where the astronomers were pretty careful, and I think this LGM1 was sort of more of an internal joke rather than something they seriously pushed out to the public. But it was a great example of where when you first saw that, you have two explanations you can invoke. you could say it's aliens, because aliens can explain anything, really. Or you can do the hard work of trying to predict what physical processes could manifest this signal. And the same thing happened not that long ago with fast radio bursts. Fast radio bursts were, again, another strange radio signal that was detected about the last decade or so. Very high-powered, very narrow frequency radio signal was coming from extragalactic sources, actually, coming from outside the galaxy. And those, again, when they were first were announced, some astronomers actually suggested this could be an alien signature of some kind. But now we think we have other mechanisms which we can explain it. And that tends to happen very frequently. Whenever something new comes along, maybe we don't initially have an explanation for it. And so aliens is just right there, just ready to go. Same with like UFOs or UAPs. It's just always there, ready to go. But if you do a bit of intellectual hard work, you can usually find some other explanation. And then you can then test those hypotheses, do more work on them. And, certainly historically so far, all of those cases have turned out to be natural, spurious events rather than the real article. Now, it doesn't mean aliens aren't out there. There probably still is a great chance of us one day detecting them. But we do have to be very, very cautious because we've been burnt so many times. And I think this is the trepidation that a lot of my colleagues have.
I recently did another interview on aliens, and I mean, this one isn't exclusively about aliens, but this last one was exclusively about aliens. And one of the books I read in preparation for this, just to see what the literature on the subject was like, was Chariots of the Gods by Eric Van Daniken. Have you read this book?
I've not read it. I know I've heard of the book. Yeah.
Yes. It's the book that spawned the ancient aliens phenomenon. Yeah. And it is funny when you think about the spectrum of things that scientists or non-scientists might use aliens to justify. You have something that is relatively responsible, like a pulsar on the one hand. And then on the other, you have the pyramids, like all of these terrestrial phenomena that are maybe difficult to understand how they were created or the root of them, but a lot of people will apply aliens to them.
Yeah, so. I wrote a paper about this with a colleague, Jason Wright, about, I think it was a year or two ago. And we point out three aspects of the alien hypothesis, which are kind of unique and lead to these kind of problems with ancient aliens, UFOs, and pulsars, et cetera, et cetera. One, as we've already said, it can explain everything. So we call this unbounded explanatory capability. EC. And then we have UAC, unbounded avoidance capacity. So it can actually always avoid you. So you might go to Mars and say, okay, I don't think there's life on Mars, but you can never prove there's no life on Mars because there could always be life just hiding underneath one particular rock that you haven't turned over. And similarly, you can never prove that an exoplanet doesn't have an alien civilization on it because who knows, maybe they've got a big cloaking device that can somehow mask their signatures from you. So it's basically impossible to falsify the hypothesis. And that's kind of a core tenet of science, that hypotheses have to be falsifiable by this definition that Karl Popper gave us back in sort of the early 20th century. So this has been two major problems. And so if you can't make headway with those two aspects, you kind of have only one last resort. And that's the Sherlock Holmes mentality that I think Avi has been writing about. And that's that you have this, whatever, once they've ruled out everything, whatever's left, however improbable, must be the truth. And so he kind of uses that logic to try and look for aliens. My critique of that would be, how can you rule out everything? Because we don't know everything. We're not omniscient beings. And that's been demonstrated with all these previous cases, that our knowledge was still evolving. We didn't know about pulsars. So if you went to that point and say, well, I've ruled out everything that we know about, therefore it must be aliens, that would be a fallacious argument, because of course you just haven't yet learnt about the existence of pulsars, which is a natural phenomenon. So this third method, I think, also fails. So you're kind of left in a really sticky situation where we don't know how often aliens hide from us. We don't know how often aliens can mimic certain natural signatures, and we don't have complete knowledge of natural processes. And that really puts you in a very difficult position. And I think it actually fundamentally challenges the very idea that SETI is even a scientific quote-unquote activity. And so I've been thinking really hard about that. And I really want to save it because I'm passionate about, from my early childhood, as we've already discussed, of the idea of looking for planets and life in the universe has been with me since I was a kid and, watching Star Trek and stuff. So I really want to make this happen and make it scientific. And so I've been thinking more recently about, this is work in progress, but I'm thinking about clustering a lot recently. And I think there could be something there where if you take clusters of spurious signatures that are localized in space or within a planetary system to around one particular star or around one particular 3D location in the universe, and you can characterize the frequency at which that signature appears elsewhere in the universe, I think you have a chance then of what we would say in sort of statistical parlance of marginalizing over your false positive rates. And so I've been working on that recently. It's not yet fully fleshed out, but I am hopeful that we can recover the fully scientific credibility of this kind of philosophical problem that I raised in the previous paper.
Just to make sure I have a grasp on this idea of clustering, you're looking for, if you can find seemingly sort of random or, I don't know, a pattern or something localized to some area, then you find that you don't see this elsewhere in space with an expected statistical frequency, then you think, oh, we might have something interesting here.
Yeah, I mean, a good example might be a simple planetary system case. So we have famous planetary systems called TRAPPIST-1. It's probably the most famous exoplanetary system at this point, except for the solar system. And it has 7 planets around it, which are all Earth-sized, or a little bit smaller than the Earth, around a star which is much smaller than our own sun. It's called a red dwarf, an M-dwarf star. And it has 3 of those planets in the habitable zone of its star. So this system has had enormous attention amongst astrobiologists and astronomers. It's really one of their favorites. And a lot of people are interested in, could that system have life? So let's apply this clustering argument to this type of system. It's surely not alone. There are surely other examples of TRAPPIST-1-like systems out there. So we could go across the sky and measure how often do we see a particular, let's say, biosignature like oxygen. How often do we see oxygen in the atmospheres of these planets in the habitable zone of that type of star? And let's say the rate was 1%. It's just, it happens sometimes, and maybe that 1% is just random chance or it's some kind of weird geological process. It's hard to tell whether that's really life at that point. But then you look at TRAPPIST-1, which has 3 planets in the habitable zone, the real TRAPPIST-1, and you see that all 3 of them have oxygen in their atmospheres. Now, you know the occurrence rate is 1% globally, but here in one particular instantiation, you have 3 in a row which all have that oxygen signature. So to me, that would really speak to the idea of panspermia, that somehow life got started on one of them and it was spreading between them through meteorites interacting, and that would be statistically highly improbable to happen by chance, given that you've quantified the rate which occurs elsewhere. So that's a pretty good, clear example of how you could use clustering to solve this problem. But I think more broadly, you can extend this to frequencies and radio frequency, to the time dimension, and also space in terms of like 3D locality within space, like a galactic empire or something. You know, someone spreading out in 3D volumes of space. And so I want to try and come up with a unified, broad framework for letting astronomers hopefully make progress with this big problem.
Well, I would really like to come back to your responsible research program, but right now, I mean, the Cool Worlds Lab show has come up, or the channel on YouTube has come up a few times in the conversation already, and we've touched on futuristic engineering and alien civilizations. And I've been going through your channel, and there is just a plethora of very exciting, cool videos out there. So I just wanted to talk about some of the greatest hits. Okay. And since we were talking about, or alien civilizations were mentioned, I wanted to begin by asking, what is the Kardashev scale for alien civilizations? That seems like a good place to start.
Yeah, sure. The Kardashev scale, it was an idea by Nikolai Kardashev, a Soviet physicist. I think it was in the 60s he came up with this idea. And he was trying to think of a way of essentially classifying advanced civilizations. And he came up with 3 numbers, type 1, type 2, type 3. A type 1 civilization is a civilization which uses the same amount of energy that is incident upon the planet itself from the sun. So essentially, imagine covering the entire Earth with 100% solar panels, and that energy would be fully used for industry, for computation, for our civilization. That would be a type 1. Of course, in practice, you'd have to leave the planet at that point, right? There's no way you could actually use that amount of energy in situ. You'd surely have to have facilities on moons and in deep space to accomplish this. So that's sort of a type 1. People sometimes extrapolate a little bit about what that really means. So they say like a type 1 is a civilization which has full control over the weather of their planet or something like that. And Nikolai Kardashev never said that. I mean, that's just it's not unreasonable to speculate that that might be what a Kardashev type 1 could do, but that's rigorously wasn't what he was talking about. He was only talking about energy strictly. And then a type 2 would be sort of you just go up the curve and you say, well, what if a civilization used the same amount of energy that the whole star produces? Not just the solar radiation which hits the Earth, which is a tiny fraction, of course, of all the solar radiation which is produced, but you somehow capture the entire sun's energy. So this gets into the idea of sort of Dyson spheres, which is an idea which Freeman Dyson had written about around about the same sort of time in the early 60s. And Freeman Dyson was imagining some kind of, not necessarily a solid structure, which I think people often imagine, but maybe a swarm of material that was around the star with maybe small chinks in the armor between them to allow for stability. And again, you'd be harvesting all of that energy and then using it for something. And what you use that for is up to you. And then type 3 would be the entire galaxy. So you essentially harvest all the stars in the entire galaxy, presumably even the black hole Sagittarius A star in the center as well, which produces a huge amount of energy. So you'd somehow have the ability to capture entire galactic level power. And it's not unreasonable. I think there's a couple of issues with Kardashev scale. One is it does feel a little bit archaic the way he's thinking about it, because he strictly thinks about energy, whereas we normally think more about computation these days and information and volumes of information, processing, things like this. So some people have criticized the idea as being a little bit out of touch with maybe the direction our own civilization is going. But at the same time, energy growth has been consistently growing by about 2% per year, more or less continuously for the last century or so. And so there is that compound interest effect of growth. And if you extrapolate that, you'd be looking at sort of the year 2300 that you'd sort of hit a type 1 civilization. By the year 3000, you'd be sort of at the level of a type 2. And then you can keep going to maybe year 10,000 or so, and you'd be presumably in charge of the whole galaxy. Of course, that doesn't make any sense because the light travel time across the galaxy is much longer than that. So there's no way you could practically hold that curve. So you'd imagine the curve eventually has to, have a knee and become an S-shaped curve. And of course, that usually is what happens with technology development. Think about iPhones. There was a very rapid exponential growth of everyone buying iPhones, but then once everyone's got an iPhone, the market saturates and it tapers off the number of purchases. So presumably there was a certain tapering off to this curve. So it's very difficult to make extrapolations about when realistically a particular year we will become each of these classes. But it has been a framework for thinking about what we're looking for when we do alien searches. So for instance, a type 1 civilization would be maybe a little bit difficult for us to have any direct evidence for. The sorts of things we're interested in would be maybe like a Starlink type constellation. So if a civilization really did need this amount of energy, they'd presumably harvest a lot of it from space using orbital platforms and beam it back to their planet, or do even data centers in space and computation in space. So that's a lot of space infrastructure. And we could potentially detect that from, using James Webb or the Hubble Space Telescope. You can imagine that producing certain signatures in our data that we could look for. It's a little bit beyond the capabilities of James Webb to detect Starlink itself. But it's not a million miles away either. You can imagine a Starlink that was maybe 100 times denser than the current version. You have like millions of satellites in orbit, and that would actually start to look like a ring system at that point. And Saturn obviously has a beautiful ring system. This would be an artificial ring system that we would have created, and that would actually be potentially detectable in our current observations. So, that's what's one possible thing to look for. And for a type 2, that would be the kind of Dyson spheres. You'd be looking for stars that essentially disappear or something. Like as this structure is rotating around, there might be gaps as it's under construction that would give you periods where the star is shining through. And then as the structure rotates back around, it would block out the starlight and the star would disappear. Or it could be over the period of like a century or 2 centuries, you notice the star gets gradually dimmer and dimmer and dimmer as more and more modules are constructed. And the other way to look for it is to look for infrared excess. If you think about a laptop or a computer, it's doing computation, it's warm. Like it's not, yes, it's pulling in power, but by the conservation of energy, you're using energy, you have to also produce that same amount of energy back out. And so that produces this kind of infrared signature that we could potentially look for, again, with like James Webb or something. And people have looked for those. We've surveyed about something like 100,000 stars for Dyson spheres, and we don't see any convincing evidence for them. And about 100,000 galaxies as well we've surveyed for these Kardashev Type 3 civilizations. And we don't see any slam dunk evidence for any of those either. So if there are civilizations out there, it seems like they don't often get to this point, which is an interesting constraint.
Or they have these cloaking devices that you mentioned earlier, and they're all over the place.
Conspiring to they have like maybe a dark forest sort of mentality where they're very nervous about detection. Yeah, and I've written about that before. One of my first papers in this subject was called a cloaking device for exoplanets, and me and my colleague actually showed how you could use a laser system to basically mask either an entire planet from our current observations, or you could even specifically block out certain atmospheric signatures. So oxygen is a dead giveaway that someone's living here, and we showed that you could actually use these supercontinuum lasers to essentially just mask out that particular signature. So even using sort of 1970s technology, we could, if we wanted to, it's not actually that much energy, it's like one nuclear power plant's worth of energy, you could mask out our signature from a particular star if we wanted to. We don't do that, of course, because we don't know of anyone else out there, but it proves the point that we shouldn't be so arrogant to assume that our observations will definitively detect them.
So many of our alien movies involve aliens coming to Earth to steal our resources that it does seem like, hey, if other alien civilizations believe that there are alien civilizations who would want their resources, then they might invest in some sort of cloaking.
Yeah, I always find that premise a little bit odd because, of course, like what is the resource exactly? Is it water? That's often what the sci-fi shows portray, but water's like very, very common in the universe.
Right.
Why not go to Europa and Enceladus or even Pluto or Ganymede? They're like 40% made out of ice. There's way more water there than there is on the Earth. And there's no one there, so you don't have to like worry about having a conflict with anybody. You could just grab onto the moon and take it out of the solar system, and you've got plenty of water. And of course, water's like abundant, and it's one of the most common things in the universe. So it's a little bit, certainly the water idea is a bit odd. I don't know of anything on Earth that is unique to Earth that you like an actual material that you couldn't find elsewhere.
I mean, even our most precious materials like gold, you can find an asteroid or something that's it's made entirely of gold.
There's even more, plutonium in some asteroids than there is on the entire Earth. So, if you wanted a rare earth metal, there's better ways to get that. The rarest commodity on Earth is life. Mm-hmm. So I don't know if that would be a resource in some way, but that would be the only unique rare thing about the Earth.
And just again to clarify, so we're not even a Type 1 civilization yet.
No, I think on the scale we're something like between 0.7 and 0.8 if you kind of extrapolate backwards. But that's sort of an extrapolation of what Kardashev originally said. He only really said here's Type 1, Type 2, Type 3, and you can sort of draw a straight line more or less through those 3 points and say like where we are. We'd be looking at sort of the year 2300 at current 2% growth, I think it is. But who knows? I mean, maybe energy usage will taper off in the near future because obviously there's already sort of an energy crisis in many countries. Energy resources are depleting. We probably couldn't burn fossil fuels until 2300. We'd certainly run out of oil by that point. So we'd have to find ways to produce vast amounts of energy. I mean, I guess the hope would be nuclear fusion would maybe come through for us at that point. And that would be obviously a huge resource of energy for us.
So that I understand a bit more about the detection or the potential detection of a Type 1 civilization. You mentioned a bit earlier in the conversation this controversy a few years ago about whether or not there were aliens on Venus. And was it phosphine gas that you mentioned?
Yeah. So this is a very simple alien life, not like a civilization.
Right. So we could, in principle, detect or have reason to believe that there are aliens on Venus because we observe a certain gas that we think might not be there unless there's some form of microbial life. But what you're saying is that if we're trying to make a claim that there's a type 1 civilization on a planet, we're making a claim not based on gases or something. It's just going to be based on energy output, and this level of energy, the amount that the planet absorbs from the star, it's just not enough energy that, given our current equipment, we could detect it.
Yeah, I mean, there's no direct way, really, I can think of to measure the energy usage of another civilization. That'd be very difficult to grab onto. Yes, you could measure the infrared power output, the luminosity essentially of a planet, but there's many ways that luminosity output could be enhanced due to geological processes. Io has a very high luminosity because of tidal heating interactions with Jupiter and its other moons. So purely measuring how much energy is coming off the planet or the moon or whatever it is isn't a very satisfactory way of claiming I've detected a Kardashev type 1 civilization. So I don't think we could directly claim a civilization is type 1. But I think you could say it's type 1-like. It's doing activities that we would normally associate with a civilization which was using that kind of level of energy. So, for instance, having orbital platforms in space that were generating huge amounts of solar panels that were then radiating that energy back down to the planet. Some kind of terraforming of the planet. Maybe we could detect that artificially. There's the heat island effect, which some people have in New York City, where we are right now, has a significant heat island effect. So if you could infrared map a planet, you would notice, you could measure the temperature of New York State, and then when you hit New York City, there would be this bright infrared spike. It'd be about 2 or 3 Kelvin hotter than the rest of the state, and that's because of all the concrete here, right? The concrete traps heat, and of course there's all this energy production and buildings trapping energy. So we could look for that. You could actually detect, you could potentially map a planet. We're not quite there yet, but maybe with a super James Webb, you could do this. You could map a surface of an exoplanet and you could see that hotspot. And then you could have actually a direct estimate of the energy usage of that city, I think. So maybe, you could say this city is sort of consistent with the behavior that we'd expect for a type 1 civilization, but directly proving its level would be difficult. I think a type 2 is much easier because that would be a Dyson sphere essentially. So I think a Dyson sphere is pretty clear proof that somebody is at the type 2 level.
And then the last thing I want to ask specifically about these alien civilization scales is, you mentioned at the beginning of your discussion of the Kardashev scale that it's a bit archaic to think of civilizations based exclusively on the amount of energy they're producing, and a more modern way of looking at it might involve information processing. So I'm curious if you have a rough schema maybe for how you would think about classifying various alien civilizations that's an alternative to this one.
Yeah, that's a great question. I think people have been thinking about different schemes. I have not proposed one myself. Certainly the number of bits being processed might be an obvious way to do it. It's not clear what the unitary demarcations would be in that case, because there's no real natural equivalent. I think the Kardashev scale is pinned down by these natural phenomena, like how much energy a planet receives or a star produces, but there is no natural computation really occurring in the universe. Maybe you could try and link it to black hole horizons, which don't really do computation, but they do have information contained on their surfaces. So maybe someone might try and pin it down to those levels. But I think it's maybe not really, it's almost a moot point. I think the problem, there's kind of this kind of sustainability paradox that exists in SETI, and that's that as a civilization presumably becomes more advanced, they don't want to waste as much energy. And maybe there's a certain point where they just don't need any more energy. If we all decide to live in the metaverse, upload our brains to some computers, then the best place to do computation would be actually really far away from the star where it's really cold. That's why we put data centers in Antarctica and Arctic, because that temperature difference gives you, with the Carnot efficiency, gives you a greater efficiency for your computation. So the most efficient place, according to this kind of theorem of the Landau limit of computation, would be in deep space, where it'd be almost impossible for us to make a detection because it'd be almost totally cold. So there's nothing really to grab onto or look for. And so the sustainability paradox really says that as civilizations become more advanced, they become quieter and quieter and quieter, and they eventually just disappear. And yes, they're still there, but there's nothing for us to look for because, yeah, maybe they've all just gone into this metaverse reality that is impossible for us to make a direct detection of. So that's a little bit concerning, but it does give me an interesting perspective about looking for aliens, and that's that perhaps the most likely civilization we'll detect is one who's the most unsustainable, because that's going to be the loudest. And I think a good analogy here is both with exoplanets and stars. The first exoplanets we detected were these hot Jupiters. They're not normal planets. Only less than 1% of stars have these hot Jupiters. They're very rare, but they dominated the first 100 exoplanets discovered. And similarly, supernovae are something we can detect from across the other side of the universe, but they're incredibly rare. Only one goes off every century within a galaxy, so they're very rare phenomenon. So how are we able to detect them? And it's simply because they're so loud. It's not that they're very rare, yes, but they're extremely shouting out to the universe, here we are. And so I think that's maybe the more likely type of alien civilization we will encounter. It's one who's probably in its death throes, that's burning all of the fuel that it has on its planet, is in the process of nuclear annihilation, and that kind of nuclear conflict would probably produce the loudest signature we could hope to detect. And I often say, who's most likely to reach out to us? Certainly if you think about the dark forest mentality, where there's a fear of reaching out, there's no real incentive to say hi to anybody, except if you're on your deathbed. And if you're on your deathbed, you need help, right? You're a civilization that you're about to hit your end. It's inevitable. You can see the future. There's only 50 years left for your civilization. There's no risk in communicating at that point because you're going to die anyway. So at that point, I think the civilization probably might make an effort to reach out to nearby star systems and say, we think we're at the end, either we need help or we just want you to know about our existence. Here's like a record of our civilization. And my personal hunch is that we are more likely to make contact with a civilization who is in a very desperate state, rather than this more science fiction idea that we have that it'll be kind of this benevolent father figure that's super advanced and will come down and teach us all this advanced technology. I just don't think they're going to be interested in us. I think that they're quite happy in their metaverse reality.
Yeah.
There's no need for them to interact with us.
No, that's super fascinating. Speaking though of this civilization that would come down like gods and give us technology, I imagine that if some relatively nearby alien civilization were on its deathbed and needed help, they might have to give us some of their technology so that we could actually get there to help them. So we might get it that way.
Possibly. Or it's also quite possible they're less advanced than us, right? Because we were capable of destroying ourselves in the 70s or the 60s or even before that with nuclear annihilation. So there may be, we often assume they're going to be more advanced than us. And that's because I think Carl Sagan had this wonderful idea of sort of, it's highly improbable that they would be in technological lockstep with us, right? It's just improbable that they'd have exactly the same level of technology. But if they're far ahead of us, my suspicion is if they've got to that point, they've probably lost interest in communicating with us because we would just be like ants or monkeys to them essentially at that point. But if they're behind us, they probably would have a strong interest in communicating with us. And anybody who's, say, 100 years behind us would be capable of radio communication, and anyone who's 50 years behind us would be capable of nuclear annihilation of themselves. So even though I agree with Sagan that such civilizations would be on the ensemble rare, presumably the majority are older than us, there must be a subset who are behind us, and that subset, I think, have a stronger incentive to communicate with us than we do with them. And it's always that asymmetry of communication that exists between two civilizations which aren't in lockstep with each other. And so we may be the more advanced civilization in that interaction. I think it's more, I suspect it's more likely that would be the interaction than one who's thousands and thousands of years ahead of us.
You said, just stepping back a little bit, that one difficulty with devising a scale based on information processing is that it doesn't have these natural benchmarks the way that the energy scale does. But one thought that occurs to me is that it might not be a question of amount of information processing that could distinguish civilizations, but just because I've spoken with people like Nick Bostrom who think a lot about superintelligence, that maybe we ought to distinguish civilizations based on the type of information processing they're capable of. And it strikes me as entirely possible that once AGI, real, genuine AGI, is reached in a civilization, they might just ascend to a different level.
Yeah, I mean, you could certainly make maybe you could take the human brain and take the number of neurons and some kind of computation level from that and compare that to the capabilities of AGI to do something like this. I do think it's a fun intellectual exercise. I think practically it's probably a bit of a moot point because I can't think of a way that we could measure the information processing capabilities of an exoplanet's surface. So it's maybe a problem that a lot of us are not thinking too hard about, because it's like, well, it'd be great if we could do that, but we're probably going to have to actually visit such a planet before that's going to be a problem. And that's maybe a first hurdle to solve before we get to that.
That's a very fascinating point, though. You're thinking about this question scientifically. What sorts of predictions can we make that would be testable? And if we classify planets based on energy scale, that's something that we might be able to devise tests for. But
that's the appeal.
Yeah. Right. But information processing, it's just an interesting intellectual exercise.
Yeah, and I think often when people talk about aliens, they do get upset with astronomers because they think we have a very limited view of what we're looking for. And folks will say, how come NASA has this policy of sort of follow the water? Wherever there's water, that's where we should be focusing our searches for life. And I've seen many members of the public get upset about that, or even some scientists saying, that's very narrow-minded because there could be life forms out there based on silicon or using different solvents than water for their life. And it's possible. It's certainly possible, but it'd be very difficult to us to imagine what we'd even look for. If you just say anything is possible, like there could be life in Jupiter's clouds, or the galaxy itself could be a living creature or something. Okay, great, but what am I supposed to look for? I mean, it's almost like saying the universe could be in the back of turtles at that point. Like, there has to be like a specific signature that we can go after. And I think we are not so narrow-minded to believe that life can only exist on water worlds, but it's a great starting point. Let's start there. Hopefully, let's get a detection, or let's maybe survey thousands of them and say, they don't have life. And once we've thoroughly exclude that possibility, then let's move on to the next most likely possibility. But surely an obvious starting point is we know that sun-like stars with terrestrial planets covered in water are capable of life. We know that with certainty because we are here on such a world. So that seems like a very excellent starting point to motivate such a search, but it does not mean it is the only place where life can exist.
I'm one of these people who happens to be kind of frustrated when I hear that scientists are only interested in planets with water. And since you probably have your finger much closer to the pulse of astrobiology than I do, is this a question that astrobiologists are looking into actively?
Yeah, sure. I mean, carbon-based and water solvents are probably two different questions.
Yes.
Yeah, for sure there has been. Solvents, people have not really directly experimented, because we don't have such a life form to experiment with, but have done the intellectual exercise of asking, what other solvents could potentially work besides from water. This is not my area of expertise, of course. That's more of a chemistry problem. But my understanding is that consistently water emerges as by far and away the most suitable, but it is by no means exclusively the only one which could work. So you could have others, but if life was given the choice of using water or something else, it would seem very reasonable that it would use water because it has so many advantages in terms of its capabilities and stability and things like this. So I think we do want to keep an open mind. And when we look at Titan is, doesn't have any water, but it has lakes of methane and ethane on its surface. And astrobiologists are very interested in looking for life in those lakes. And in fact, we have a mission called Dragonfly, which has been approved and will be landing there in the next decade, which isn't directly searching for life, but we'll look for the molecular traces of the sorts of organic molecules that life could produce in the atmosphere. So we're investing energy into that question for sure. But given all bets being equal, I think our hunch is that if you only have, $10 million or whatever to spend on a certain search, you probably want to put $9 million of those dollars betting on water. And then you don't want to discount the other bet, but maybe that's more of your stocks and bonds type policy, right? You put your high risk investments, you'd want to have something there as your hedge, but probably the bulk of your investment portfolio, you want to put on the most likely thing to generate a return. And it's just the same as sort of financial thinking.
Are you a fan of alien, like sci-fi movies?
Yeah.
Have you seen Battle Los Angeles?
I don't know if I have. I think is it because there was the claim that there was actually a real battle, wasn't there?
Right.
In the 50s of like, but
Yeah.
actually, I think it turned out to be some kind of like military exercise going on.
Or so they say. But yeah, but yeah, I think that's probably where the title comes from. But I don't know when it came out, maybe 10, 15 years ago. It stars Aaron Eckhart is his name. I highly recommend our listeners or viewers at least check out the trailer. It was one of the first trailers I remember that starts with that bum that just was in all the trailers.
Horn.
Yeah, exactly. But the reason that it comes to mind, one is I think the premise of that movie is that the aliens invade because they want our water. I might be wrong, but we discussed why that was silly. But the other reason is that they are in essentially technological lockstep with us, notwithstanding the fact that they managed to get to Earth, but they arrive outside of Los Angeles and other cities, and they basically shoot guns and have rockets, like rocket launchers. And this is what came to mind when you brought up that Carl Sagan quote that, or it wasn't a quote, but an idea at least, that it's very unlikely we would find other alien civilizations that are in technological lockstep with us. And I wanted to ask you a bit about that, because the two reasons that come to mind for that, one maybe less important, is that just if we're evolving on completely different planets, assuming we have very different makeup, it's unlikely we would have to develop the same sorts of technologies. But more importantly, and I think that you mentioned this, is that the universe is a very old place and our civilization is relatively young. Is that the main idea?
Yeah. So it's really a timescale question. Yeah. So the universe is 13.8 billion years old. Our own sun is 4.6 billion years old, and the Earth is about 4.5 billion years old. So that's obviously a vast timescale compared to the lifetime of our civilization. Certainly technological civilization, the Industrial Revolution, you might put it sort of 150 years ago or so. So that's a very, very short fraction. 150 years divided by 4 billion is a minuscule number. So the idea that even if another star was born at the exact same time as our star, and it had a planet develop at the exact same time, it took essentially 4 billion years for life to undergo this presumably somewhat stochastic, random walk, in an evolutionary sense, to get to us. So it'd be very surprising if that evolutionary timescale is not just comparable, but identical in every single instance on other planets, because presumably there are differences between these planets as well. And then on top of that, stars aren't all born at the same time. There is obviously our star was born within a cluster, within a stellar nursery, so we would have siblings. Actually, there would be other stars that were born at the same time as us. Actually, an interesting question in astronomy right now is to try to find those siblings. We don't know where they are. They've probably been scattered across the galaxy by now after 4.5 billion years, like sort of stirring jam and porridge. It all gets kind of mixed up in the galaxy over 4 billion years. So it'd be really fun to try and find those siblings. But of course, the vast, vast majority of stars were born at completely different times to us. Some are billions of years older, some are billions of years younger. So the probability that they would another planet would happen to have had such a similar history to us is just presumably, I don't think it's hard to do the calculation quantifiably, but it's presumably a very tiny number. We actually did a paper about the age of civilizations a while back in my team, and we came to the conclusion that most civilizations out there are probably far ahead of us, in fact, in terms of their age. And we're really thinking about the analogy of sort of trees in a forest. If you walk into a forest, there's lots of trees which are young and there's lots of trees which are old, but actually most of the trees will tend to be fairly old. And the reason is because old things just stick around longer. So if you start with a 50-50 mix of, say, young civilizations and old civilizations, and you spawn them equally in the galaxy, the young ones, let's say, only last for 100 years, and the old ones last for 1,000 years. That's for 10 times longer. So yes, you created an initially equal mix, 50-50 of young and old, but the young ones pretty quickly die out. And yes, you can keep repopulating them, but the old ones just persistently hold on and stay there. And they keep repopulating as well at that same rate of 50-50. So you very quickly end up with an overabundance of the old civilizations in such a mix. And we sort of showed this in a computational simulation and did some sort of mathematics to back that up. So, regardless of their probability of interacting with us, I think it's probably true that we are most likely, if there are civilizations out there, and maybe there aren't, I'm sort of open to that idea as well. We may be alone, as I've talked about on the channel a few times before. But if there are civilizations out there, I think it's most likely that the majority of them would be older than us. But there would be some small fraction which are younger than us. And as I said, I think they're the most likely ones that would reach out to us. And the older ones would presumably have sort of moved on from the interest of communication, because otherwise why wouldn't we have seen them by now? Because surely they would have the capability of beaming us very strong signals if they wanted to.
I know that cosmology isn't your area of expertise, but in the first instances after the Big Bang, there was no room for life, even though, the universe expanded quite rapidly. Just the state of what was going on, life couldn't have formed. I think you said the universe is 13.9 billion years old? 0.8. Do you have any idea when the first life could have arisen?
Yeah, that's a fun question. The real question is, how fast can you build a planet around a star? We think the first stars probably started forming within sort of 100 million years after the Big Bang. But those first stars were probably very different from the stars that we have today. Those population 3 stars, as they're sometimes called. It's kind of weird. We call them population 3, but they're really the first generation of stars. Just sort of another example of astronomers giving things bad names. But these population 3 stars would be behemoths compared to the stars that we have today. They would be absolutely gigantic. They'd be like the James Deans of the universe. They'd sort of burn fast, die young, and they would be the engines of nuclear fusion that created much of the heavy elements that then were distributed across the galaxy and led to the second generation, third generations of stars to form. So those first stars were probably extremely pristine in terms of their chemical composition. They're probably more or less pure hydrogen and helium, which is the only thing the Big Bang really produced. It produced very trace amounts of like lithium and some other elements, but 75% hydrogen, 25% helium, more or less. So those first stars would have looked like that. And then as time goes on, there's a chemical enrichment to the universe. And once there's enough heavy elements, things like iron, carbon, oxygen, silicon, things like this, you can start to build planets, presumably. You can start to have dust grains. Those dust grains can then coagulate and form planetesimals, which can then join together to make planets. So presumably the very first stars did not have planets. And we actually do have somewhat evidence to support that idea, even though we can't detect or even probe the existence of stars that far away from us, which would be billions and billions of light years away from us. We certainly can't do that yet. There are some very massive stars that we can, in our own galaxy, which are still around or have recently been born and are in existence, and we can probe planets around those, and we don't find planets around those. So stars which are even a little bit more massive than the sun will live for about 10 billion years. The more massive you make the star, the shorter its lifetime. Stars which have lifetimes of less than about 100 million years or so, which are the more massive stars, those just do not have planets around them. So presumably the time scale to build a planet is sort of comparable to the lifetime of the star itself at that point. And they just are not around long enough for planets to be made, even if they have the heavy elements to begin with. So probably, I think you'd be looking at about 1 billion years of cosmic history needs to play out to have the first planets emerging. And there is some evidence we can actually age some of the stars that we've detected planets around. And I think the oldest, the record holder, is about 12 billion years old. So we know of a 12 billion year old star that has planets around it. So that's encouraging to my idea that about 1 billion years after the beginning, you could have planets. And so, yeah, presumably if it takes 4 billion years then on those stars to develop intelligence and evolution to take place, then somebody could have, 7 billion year head start over us, which is just ridiculous in terms of, I'm a little bit skeptical that such civilization could truly persist for such a timescale. But one of my colleagues, Adam Frank, who's great, he's been on like Lex Fridman's podcast and many other great podcasts as well. And I encourage you to chat with him at some point. He's really fascinated with the question of what does a billion-year civilization look like? How do we even, conceptualize such a thing? And what would we be imagining their activities to be like? Because presumably there are some, if in galactic history, there's no reason why that couldn't happen.
At the outset of your response, you said something like, the way you answer this question is you think about how fast can a planet form around a star. And I think that that's a really interesting assumption that you're making, that we need to answer this question. And it might be a correct assumption, but I mean, for instance, we know that at least in theory, it might be a problem for some physicists that things like Boltzmann brains could form spontaneously due to thermodynamic fluctuation. So for our listeners, if the universe is big enough and goes on infinitely, you would expect that these brains would just spontaneously form and think that they are alive and had a whole history. So at least in some physics scenarios, something life-like could form without a planet. But is there a more general reason why we would expect life, or most life at least, to form on planets and not elsewhere, like in stars or in the interstellar medium?
Yeah, that's a good question. So to break that down a little bit, for the Boltzmann brains thing, I'd say it's a fair point that in an infinite universe, you could have these very strange, spontaneous emergences of Boltzmann brains, but they would be transient. Such a thing is not stable, so it would have almost a moment of consciousness, and then it would immediately destabilize. So such a thing is not a stable configuration that can last in the universe for a long time. So,
well, interestingly enough, I think that in this infinite universe, you could have a Boltzmann galaxy emerge spontaneously, almost, and that would be presumably a more stable configuration than just a Boltzmann brain in the vacuum.
I'm still not sure if that would be a stable configuration, but
I'm not an expert on this.
I think any life form requires an energy processing. It's basically exploiting entropy is essentially what it's doing. It's working against entropy for a short time, which requires a consistent energy source and metabolism. So it'd be very difficult to imagine how you could have a conscious entity burst into being that would have any kind of sustainability in terms of the energy processing. But you could imagine extremely contrived, not only a Boltzmann brain emerging, but an entire universe around it to support its own existence as well, I suppose.
Exactly. I mean, that's the problem. If you have an infinite universe, then you have to assume that these things will happen.
True, but we don't actually know the universe is infinite, and we certainly don't. We certainly know the universe hasn't had infinite time, which is also somewhat necessary. I think the Boltzmann brains is a subtle issue. A lot of people really are concerned about the.
I'm not suggesting that they're a likely thing we need to consider when talking about aliens. I'm just saying that they're possible.
Yeah.
So they're
seemingly possible.
Seemingly
we don't
possible.
know if it's actually possible, but if you look at the theory naively, it does seem to suggest that is a possibility. But leaving brains aside, in terms of the planets, I think I should be a bit clearer there. And that's that it's not so much that you need a planet, although that it does seem a good starting point for life forms to emerge. You need heavy metals, we think, because but planets are essentially a collection of heavy metals into one location. So you need the chemistry of life that we know of is all based off carbon. And that's because it's a molecule, an element which can have a huge number of chemical molecules. But silicon could possibly also serve that purpose, and maybe some other things as well. But certainly hydrogen and helium are not interesting at all for life. Helium's a completely inert, noble gas, so it's like the least useful thing for life you can imagine. And hydrogen is just extremely simple. Hydrogen by itself can only form hydrogen bonds. That's it. You just have hydrogen gas and helium in the universe. So it's very difficult to imagine how something that was only capable of 3 states or so could possibly form a chemical system that was capable of life. So you need the heavy elements. I think that's maybe not too controversial to say. And the heavy elements come along with the planets. So essentially, once the stars start manufacturing these heavy elements, they then coagulate into planets. And so they sort of come side by side. Once you've got the heavy elements, you also start forming planets. So maybe that's a good clarification. But I think it's also quite reasonable that you'd expect there to be a substrate surface where you could concentrate the chemicals. Because yes, the sun has iron in it. And yes, the sun has nitrogen in it, and other heavy elements, but they're distributed across an enormous volume, of course, of the sun, which is just truly a vast volume. It's like a million Earth volumes. So the probability of those elements combining together to form a molecule, which of course is also impossible because of the heat of the sun, which does not allow for those molecules to be stable anyway, poses a major problem. So you really need to concentrate things together. And that's kind of a problem why a pure ocean world might be a problem. If you have just a pure ocean with no surface on it, no land surface, it's a little bit challenging to imagine that 3-dimensional space, how molecules could come together. On a surface, it's a 2-dimensional landscape. And so you kind of collapse one of the dimensions down and you greatly increase the probability of concentration. So a lot of astrobiologists tend to think that some kind of substrate surface is a prerequisite for getting the chemical densities necessary to have complexity.
No, all of those reasons you gave are extremely compelling to me. And it makes sense in a similar way to why we would be looking for planets that have water. It's just, one, we know that life can form on planets, so that's a great place to be looking for.
But I want to be clear that we don't know. I mean, I can't say.
Well, we know that life has occurred on this planet, so we know that it can occur on other planets.
But we don't know what the limits of life are outside of the Earth. And I think I want to be clear about that, because I think sometimes scientists can come across as claiming that we know things that we don't have any evidence for, because we don't have any evidence for what life can and cannot do beyond the Earth. This is only extrapolation and speculation at this point. I want to be clear that I'm speculating about what life could do outside of the galaxy or outside of the Earth based off the rules of physics and science and chemistry that we know of. But I think all scientists are always thrilled when we're surprised and something different happens to that which we expect. That's when science is its most exhilarating. So I by no means discount these possibilities of exotic forms of life that we haven't yet imagined. But in terms of purely the pragmatic act of focusing our search on something which we think has the best chance of success, in terms of that sort of stocks and bonds mentality, I do think it's prudent to focus on things which, at least initially, have a resemblance to ourselves.
Yeah, and I would just like to clarify that I'm not intending to portray you as believing any of these things. It's interesting speculation.
Right.
And you said a few minutes ago when we were talking about us not being in technical lockstep with most aliens that we would expect that most alien civilizations would be far, far older than us. So again, this is speculation. We don't have evidence for this.
Yeah.
But does it seem to you more likely than not that the universe would be filled with lots of ancient alien civilizations?
I tried to remain very agnostic about that. And so this kind of comes back to these videos I've talked about and sort of I've championed of why we might be alone. And I think we just have to be careful for the reasons I alluded to earlier on this interview about experimenter's bias. If I said to you, yes, I'm convinced the galaxy is filled with advanced intelligent civilizations, I'm preloaded, right? And that's dangerous. As a scientist, my job is to be objective and to try to be open-minded about all the possibilities. And so if I decide the universe is definitely filled with intelligent civilizations, before I have any evidence to support that belief, then I think I'm failing as a scientist. I think my job is to purely be driven by evidence and see where the evidence takes me. before coming to conclusive determinations about what's out there. So, and there's many ways we can imagine the universe being empty. It's not that hard. Perhaps the processes of even producing simple life are incredibly unusual and rare. And the nature of the Earth itself is incredibly unusual and rare. Maybe having a large moon, just the right fraction of ocean, and just the right kind of star and planetary, a stable planetary system. Maybe all of those elements are extremely, extremely unusual. And yes, in an infinite universe, there will be other examples, but I would claim that's kind of a moot point. If there's another Earth-like planet with a civilization on it that's beyond the Hubble horizon for which we can possibly interact with, then it's almost meaningless. It's like saying, in another dimension there's a civilization. Like, great, but there's no way for us to interact with that thing, at least if we believe the speed of light is a finite limit. So I think that the more interesting question is there somebody in the possibly interactable volume of space within us, which is presumably the galaxy, or even closer in than that we've had the emergence of simple life? I think that's an experiment we can do. James Webb is almost the precursor experiment to that type of work, of looking at exoplanet atmospheres and seeing what kind of organic molecules we can detect in our atmospheres. And we are hoping to build a successor to that will actually do the life detection experiment itself. And then, of course, with SETI, we're asking the other end of that question is whether those life forms eventually develop into something which we could commune with, or even just detect the presence of technology. But I want to be, I think when we imagine another civilization, we kind of imagine that they're going to be like a humanoid figure, because we see that in Star Trek and things, or sci-fi. But they may be so alien to us that the idea of a communication or any kind of interaction is never going to be particularly satisfying. We can't really communicate with other animals on our planet in a particularly satisfying way. Like even dolphins and humpback whales, we still can't decode fully what they're saying to each other. So I think the idea that we will be able to interact with an alien who's potentially completely genetically different from us, and a whale and a dolphin, they're very closely genetically related. There's probably only a few % difference genetically between us. So, and even then we struggle for communication. So it does make me a bit pessimistic that we will ever have a satisfying interaction with an alien civilization. And I always say, for me that's a bit humbling, because every single human being that's on this planet, we are, me and you are going to be able to understand each other better than I think any alien ever will, because we are the same species, we speak the same language, we have the same culture, we have the same upbringing in terms of sort of the environment and that we've come up in. So I think it's, if you want to have a meaningful interaction with another entity, just talk to another human, because you can travel for a billion light years any direction, and you're probably not going to have such a meaningful interaction as you can with another humanoid.
Mm-hmm. Yeah, this reminds me now of that movie where I believe it's Amy Adams. The whole plot of the movie is figuring out how to be in contact with these aliens, and I'm sure that given what you've just described, that's even a very fantastic scenario. We probably wouldn't even have that much in common with.
Yeah, I mean, there's a certain level of shared cognitive capability, right, that is displayed in that story. And it's not obvious there would be any shared capability. I mean, an example I like to give is a fungus. It's perfectly possible you could have a planet that develops a fungal life form on it, and it totally takes over the planet. The surface is just covered with this one fungus, and that fungus does not know of any other life forms because it's the only life form. And so even the idea of communication with another life form would be, or just another life form in general, would be a totally bizarre concept to it. And yet it could have this hive mind superintelligence that far exceeds that of ourselves. And the things it's interested in are solving math theorems that are far beyond our comprehension. And so the idea that we would have any kind of meaningful interaction with this fungus planet is maybe a little bit fanciful. Yes, we can recognize and respect its intelligence, but it's probably going to be that's about it. There's probably not going to be a very satisfying interaction with that thing.
Very interesting, just because I know from other conversations I've had that our very unique human intelligence, its evolution was shaped by the need to communicate and predict the way communicate with and predict how other organisms would work. So it's interesting to think of a super intelligent fungus that evolves its intelligence without any need to communicate.
Yeah, and of course there's no real identity. I mean, one thing I've been thinking about recently with our own civilization, the challenges we're facing, is I think humanity has a strong need for a sense of distinction and identity. Like the idea of just being part of a fungus kind of disturbs us. Like we want to have a certain selfhood that stands out. And so that could be that you support a certain team and you have a certain hobby and, hey, here's the way I think about it. We all have like to own a certain perspective. We don't just want to be part of a uniform, homogenous, gray slush of non-identity. At least most of us don't like that idea. And so that's, I think, a double-edged sword for humanity. It leads to enormous ingenuity and innovation because it causes competition between us. And so people want to stand out by being the smartest, the best, the fastest, the first to do X, Y, and Z, and lead to that selfhood identity of I am this person. But it also leads to enormous tribalism and negative competition between us. It leads to war and conflict. And so it's interesting thinking about other civilizations, whether this is an aspect they will have too. Is it necessary to have this kind of social structure of individuals who compete with each other to lead to technological innovation, to lead to that type of civilization we imagine? Or is that recipe ultimately doomed to failure? Or are we ultimately going to blow ourselves to oblivion because of the fact we can't talk to each other? We're so polarized, we're so competitive with one another, and we're so trying to force our identities upon others and win out against other identities that it causes us to self-destruct. It's not obvious to me. We're playing the experiment, and it's a kind of an interesting, simulation, if you like, as to what happens under such an environment. And maybe the fungus just never develops an intelligence that's comparable to us because it never has that drive of competition between itself to innovate and go further.
It's interesting that our conversation has led us to this topic of the self and the importance of identity and communication, because what's fascinating about this question of is there alien life out there, one thing that's fascinating about it, it's not necessarily the very intellectual question, can non-carbon based life arise? It's a question about whether we're alone out there, if there's something that we can communicate with, if there's something else out there. And I think for that reason, it's worth taking a bit of time to talk about this question that you've already raised, are we alone, before we get back to some of the other issues we were discussing. And that raises this topic of the great filter hypothesis. What is this hypothesis?
Yeah, so I mean, when we look out to the universe, we don't see galactic empires. We don't see loud radio signatures of civilizations. And so this is the Fermi paradox. Why, if it seems reasonable, and it is an assumption that if it's reasonable to expect life and intelligence to develop, that's the assumption, then how come we don't see evidence for it? That seems in conflict. So the paradox is that under this particular assumption, you have contrasting evidence against that supposition. So the great filter is one of the resolutions to this, and it suggests that there are certain bottlenecks in the emergence of intelligent life and ultimately to a radio loud civilization that greatly reduce the probability of making it to the next step. So that probability could be the great filter, could be that life itself is just an incredibly unusual phenomenon, or maybe life is pretty common, but the development of the eukaryote cell or something like this, some kind of high efficiency metabolism, is an incredibly unusual evolutionary adaptation. Or it might be that the great filter is the development of hominids or intelligent life, technological species, opposable thumbs, whatever you want to call it, something which can manipulate the world around it and produce technology. So it's possible that any of those previous things are the great filter, but the great filter could also be ahead of us. It's something we've not yet encountered, but is imminent, and that would be maybe some kind of self-annihilation scenario through, maybe nuclear war or AGI takes over or something like this. Or it could be that the Great Filter is even further ahead than that, and maybe civilizations have this kind of dark forest fear that they just choose not to engage in that kind of interaction. So there is some filter. Doesn't have to be existential, but there's some filter which stops the universe being loud, essentially, in terms of why don't we see these clear evidence for civilizations all around us, because there's 100 billion stars in our galaxy alone. So there's plenty of opportunities for that to happen, and yet we just don't see any evidence for it.
Is there are there a few potential great filters that you think are more likely than the others?
I think right now, a lot of us are concerned about one being ahead of us, of course, because that seems the most not only relevant to SETI, but also relevant to our own existence, which is probably the thing we care about the most above all else, is our own continual survival. And so I think there's a lot of fear. Certainly these days, a lot of people are talking about AGI, like if you chat to Max Tegmark, and if you've chatted to him on the podcast before, but he's been a big advocate of constraints and limitations on the development of artificial intelligence technology, because we are creating an intelligence which would far exceed that of our own. And certainly if you look at the history of the Earth, when a super intelligence first emerged, which was ourselves, it led to the mass extinction of thousands of other species on this planet. And we really honestly don't seem to care that much about other species. We don't lose a lot of sleep about the loss of all of this, of animal life and forests that we've destroyed in order to build cities and roads, because that's more important to us. And so the fear is maybe an AGI just won't, if it treats us the way we've treated other animals on this planet, it doesn't necessarily look that good for us.
It's interesting. I mean, the way that you frame it, I have always thought that this thought experiment of the paperclip maximizing AGI that wipes out humans to make as many paperclips as it can is far-fetched. But now that I look at it as, oh yeah, we annihilated the dodo bird to maximize just like filling our bellies, it doesn't seem so crazy anymore.
I don't think it's an unreasonable concern. It doesn't mean that I think it's likely necessarily to happen, because who can really even quantify the odds of such a thing? None of us are Nostradamus. We can't predict the future. But I certainly think it's a reasonable and rational concern to have. And every time there has been interactions both with humanity and other animals, but also between human civilizations where there's been a technological asymmetry, think about the colonizers of the Americas, it ended up being pretty disastrous for the indigenous people. So I think that was what Stephen Hawking was always concerned about with alien contact, was, we should not be engaging in messaging. We should not be broadcasting our presence, because they're going to be ahead of us. And when you look at our own history, that's always been disastrous when there's been contact between asymmetrical technological civilizations. And I think it's interesting that we are not prepared to engage in METI, the messaging of extraterrestrial intelligence. We don't have any systematic program for doing that. And most people you chat to would have deep reservations about such a program because of that fear.
Transmitting signals to it.
Of saying to someone, hey, come over here we are, here's our address, why don't you swing by and say hi? A lot of us are not comfortable with that idea for rational reasons, but we are strangely okay with the idea of developing essentially the same thing in-house, right? We are producing a potentially far more advanced intelligence than our own intelligence on our own planet. It doesn't even have to travel here. We're making it right here on our doorstep. And we don't know what it's going to do when it has its own agency. That's the big question. What's it going to do with this agency that we haven't yet achieved, but we are aiming to bestow upon it?
So is this something that you are personally quite worried about?
I think it's, I think I worry about it mostly from not so much of an existential perspective, but more from an intellectual angle. I think we are becoming increasingly dependent and intellectually lazy in terms of our mental facilities and faculties, in terms of depending on these machines. Certainly as an educator at Columbia University, we see students using ChatGPT more and more for their assignments, and we're trying to think of ways to do that in a constructive manner towards their education, because of course we don't want to pretend these tools don't exist, because they're going to go into the real workplace and people will be using those tools. So it's kind of, you can't put Pandora back in the box, it's out. So that we have to concede that it exists. But at the same time, we want them to develop their own critical thinking, because ultimately that's the whole point of education, is the ability to have critical thinking. But once we have intelligences which can do the critical thinking for us, it's incredibly easy to just hand that all off. And then what's the fate of humanity if we stop learning how to think? That worries me more, that not that we become extinct in terms of our biological survival, but intellectually we become almost extinct in terms of our desire and even capability to think for ourselves anymore, because we just start deferring everything to these AGIs. So that worries me more.
I'm with you that, and this isn't in response to what you just said, but something you said a few minutes ago, I'm with you that the development of AGI could see that as a great filter for like type 1 civilization, something like that, for instance. But personally, I find myself much more concerned about abiogenesis being a major great filter, because again, ostensibly, unless you believe in God and God created life, then you think there's at least one instance, namely the Earth, where life arose from non-life. But we haven't succeeded in recreating life out of nothing on Earth. And it just seems quite possible that it could be exceedingly, exceedingly rare, and we've just really underestimated this.
Yeah, I agree. And I think that's, I'm pleased that you express that view, because it's not a commonly held view. I think a lot of people tend to assume that what happened here by the sort of principle of mediocrity and Copernican principle logic must occur elsewhere. And I think that's a very fallacious argument when people make it using the Copernican principle in that way, because you can't really invoke the principle of mediocrity when it depends upon statements where your own existence is predicated upon it. So, I mean, a good example would be like, we have an oxygen atmosphere. So by the principle of mediocrity, all the other planets in the solar system, or a lot of them, should have oxygen-rich atmospheres, but none of them do. Or they should have liquid water on their surfaces, because we have it. None of them do. So the reason is because we have to live on a planet where those things exist, because otherwise we couldn't be here. So there's a sort of a weak anthropic principle effect playing. We have to live in those places where the conditions were suitable for our own eventual emergence as an intelligent being. And so it's not surprising that we live on a planet where life started quickly on the Earth, because had life taken 3 billion years to get going, rather than the fairly rapid time it took on the Earth, evolution wouldn't have had enough time to play out to get to us. It takes about 4 billion years in terms of our own history to get to us. But the Earth will not be habitable to complex life in about 1 billion years' time. So you have to get life going quickly if you want to get to us for sun-like stars. So people often invoke our existence and the early start to life as evidence that abiogenesis is easy, and I think that's a dangerous argument. And I actually formalized this with a statistical model that I published in the Proceedings of the National Academy of Sciences about 3 years ago now. And I came up with this formula where you can sort of plug in how long did it take life to develop, the earliest evidence we have, how long is the Earth habitable for, and when did we emerge? When did intelligence emerge? And so those are the three numbers. And I plugged those three numbers in, and it gave an odds ratio that abiogenesis, the origin of life, is a quick and easy process versus a slow and difficult process of about 3 to 1. So it's about 3 times more likely that life is easy versus life is hard. But that's not overwhelming. Normally in science, we want sort of 10 to 1 odds or greater before we really believe the hypothesis. So at that point, I was very agnostic, and I said, look, it's 3 to 1, so, it's interesting, but not convincing. But my opinion did change recently, because the paleontologists and the geneticists have refined that date. And so they've now pushed it back to 4.2 billion years ago that they have the earliest evidence for life now. And this is through genetic heritage dating of the last universal common ancestor, Luca. So that's the thing that we're all genetically related to. And they can date that to have been living 4.2 billion years ago.
Wow.
And the Earth had oceans 4.4 billion years ago. So within 200 million years, life was present. And not only, that's not when life began, that's when life already had a pretty major foothold on the Earth. So that is so early, it actually kind of overwhelms even this concern that I had about the bias there. And it actually leads to greater than 10 to 1 odds for the first time.
Wow.
Almost irrelevant to how long Earth, in fact, it's totally irrelevant to how long Earth has left to live. So even if the Earth ends tomorrow in some kind of asteroid event or something, it's still true that the odds are greater than 10 to 1. So that seems quite robust to me. And so my opinion has shifted. However, it's still predicated on the existence of a true Earth. And that may be very unusual. To speak to your point about maybe abiogenesis is rare, maybe true Earth analogs, having just the right conditions to cook all this stuff together in the right way, is an exceptionally infrequent occurrence in the universe. And that's totally plausible. We don't have a way of evaluating that occurrence rate just yet.
I should also stress, and you know this well, that the human mind is ill-equipped to deal with large numbers, probabilities, percentages. And when I say we haven't succeeded in abiogenesis in the lab, okay, we've been probably trying this in a few labs for 100 years or so. This is very different from the vast distance scales when you just cover the entire Earth and the hundreds of millions of years and the various terrains in the Earth, on the Earth in that time period. So there's really no comparison.
I mean,
at
it's
all.
a multi-million year experiment, and we just can't. We're trying to get up to that point. There's actually some really interesting work by Lee Cronin, who's been sort of automating these chemical experiments so you can have these robots that do very rapid chemical experiments to try and speed up that time scale, right? So you can kind of do 1 million years in a day in the lab, something like that. That would be fantastic if we could get to that point. So I'm optimistic that the lab experiments will get to the point where we can actually ask that question more sensibly. But so far, currently, you're right. The current lab experiments are just not particularly constraining in terms of, you can't really say either way. The most success we've had with lab experiments is synthetic life, where you actually take existing life and you strip out the genome, make it as simple as possible, and you see what can still survive. But of course, that's starting from something which is already here. It's not necessarily speaking to the ease at which life gets going from nothing.
While it's interesting to talk about whether or not we're alone in the universe, it is certainly much less fun than to talk about the other possibilities. And you mentioned METI, so messaging, extraterrestrial intelligence. You also mentioned SETI. So SETI actually exists, METI doesn't, I take it?
Well, I guess there is a SETI program. Right. There is a SETI Institute, and there's the Breakthrough Listen program, which is an activity in SETI. SETI, I think the field has been trying to rebrand SETI a little bit. It's done this in the past. Actually, SETI used to be called CETI, Communication with Extraterrestrial Intelligence, and rapidly it left that name because people realized that the idea of communication would be very difficult. Maybe the idea of actually communing is simply impossible, but we could at least know that they're there. So that's why we switched to SETI. And more recently, we switched to sort of techno-signatures as a branding, because I think SETI has this historical legacy of being an activity in radio astronomy, where you're trying to detect radio waves. But the Earth is becoming radio quiet over time. We're increasingly switching to microwave technology, which is very short field for submillimeter and for 4G, 5G, LTE type communications. And then we're using lasers and fiber optics for high bandwidth communication. So it's not obvious that a civilization would be radio loud anymore, as we used to think. So techno-signatures is this broader landscape of, what could they do with their technology that would be detectable? That could be their satellite systems. It could be the heat island effect. It could be solar panels. could be laser emission, space rockets, whatever you want. So that's, I think the field has moved on from that. METI, there's no such, as far as I'm aware, a METI institute or an active, well-funded program in METI. And I think, there has been efforts at METI. There was a famous Doritos advert that was broadcast to a nearby star. There's the Arecibo message that was sent out to a few stars. So there's a few efforts. The Pioneer spacecraft, the Voyager spacecraft have these plaques on them, which I guess you could call an activity in METI because they are an attempt at communication that another alien civilization could one day recover those spacecraft and learn something about us. And for me, I'm actually interested in METI. I'm part of a project called the Golden Record Project, which is sort of, the Golden Record was on the Voyager spacecraft. And it had some images, it had some music, not a lot of information, but a little bit on there. And I think we're trying to reinvent that project to create an open source golden record that really wouldn't be a physical record, it'd be a digital archive that could have huge amounts of data stored within it. And we want to make this open source box that hopefully private space industry could attach to their spacecraft and hopefully get these spacecraft out into the solar system and maybe even beyond in the future, so that there's a larger footprint of these devices left. And my personal hunch is that an alien civilization is unlikely to encounter these, but I think there's two good reasons for doing it. One is it forces us to think about what we want to actually communicate to the civilization, like who speaks for the Earth, what are the things that we think are appropriate or inappropriate to share. And two, I think it's actually likely, or possible, I should say, that somebody will discover it, but it will be a descendant of ourselves in the far future, or another Earth-based creature. Maybe human civilization will have its sunset in the next few thousand years and will, become a tribal people again or something. And eventually another creature will emerge as the next civilization in maybe 50 million years from now or something. We can imagine another creature like an octopus or a dolphin emerging as the next civilization. And they may have a space program one day and venture out into space and discover our spacecraft and think, hey, I think there might have been a species before us that lived on the Earth that was intelligent. And actually they've left these tombs for us to discover. So I'm actually think that's the most likely method, in my opinion, of alien communication. It's not alien in terms of extraterrestrial, but it is alien in terms of it's a completely independently or semi-independently biologically developed intelligence out of ourselves. And so I think that's a fascinating possibility that we could commune with them in the same way. You think about the monuments that like the pyramids or Stonehenge, they are artifacts that were left thousands of years ago left as an attempt at a memorial, like remember us, here's the things we did, remember something about our civilization, our culture. And there is an opportunity, I think we have, to be remembered and not completely forgotten, not just simply erased from the record of galactic history, that another civilization might know who we were. And maybe that's not what we hope for. Maybe it'd be nicer if we had a two-way communication. But I just feel like that's a very fanciful, science fiction-y ask. I think the most plausible, practical thing I can imagine being possible is this contact with a future descendant.
Something interesting about that, though, goes back to, you used the word technosignatures when talking about SETI. Now that I'm rethinking what I was saying, what I was going to say is we might not think that these dead civilizations would give off the same sorts of technosignatures, but that's just because I'm thinking of our monuments as things like the pyramids that aren't Dyson spheres, for instance. But that actually brings me to another question. So we started off the conversation a bit by talking about the Cool Worlds Lab YouTube channel, and we've discussed many topics that have been featured on the channel, but one video in particular I think is called "What is an Alien Megastructure?" And we've spoken about one of them, which is the Dyson sphere. But I'm curious, one, if there is a sort of definition of what an alien megastructure is that you operate with, and whether or not we might talk about some other types of megastructures that might give up technosignatures.
Yeah, I think Megastructures is essentially some grand engineering project that has been produced by a civilization. I don't think it has a strict, rigorous definition, but it's something that I think we assume is presumably detectable from afar. And that megastructure could be something on the planet itself. It could be like a space elevator or something, or a tether connected to a space elevator that produces, or an artificial ring system around that planet. We sort of talked a little bit about the idea of Starlink eventually becoming almost like a ring system. The Clark Belt is an obvious place where you might imagine something like that happening. The Clark Belt is the orbit of a geostationary orbit. So there's a good reason why we like to put satellites there. There's actually a huge overdensity of satellites there. The Starlinks are not there. They're in low Earth orbit. But if you go further out, you get to geostationary orbit. And then you have a satellite which sits above the surface at the same location at all times. That's really useful for communication. So we might imagine looking at another planet and noticing that there is an overabundance of material at the Clark Belt location. And that would be extremely suspicious. I think that would have to be a technosignature at that point. There's just no way naturally there's any preference for putting material at that location. And it would essentially reveal the detection of a communication network for that civilization. Other structures could be to fight climate change. Not climate science, climate change. Climate change is obviously a big problem for ourselves, and we're thinking about geoengineering solutions. And one such solution would be to put giant mirrors in space that could potentially block out a large fraction of solar light and cool the Earth down as a result. And the obvious place to put that would be the Lagrange point that sits between the Earth and the Sun. And so again, that's a very well-motivated location. It's not a stable position, actually. It's only metastable, so it requires station keeping for something to stay there. So again, if there's a large collection of material there, then you know that there's someone who's deliberately putting it there, because material just shouldn't hang out there naturally. So I think that's there's actually been some projections of what that material might look like in our data. And there was even a science fiction movie I really love. There's a Canadian movie, it's an independent movie called Clara, where it's about a scientist who has the idea of looking for that signature. And actually, the movie makers worked with Eric Gaidos, who is an astronomer who proposed this idea of how a civilization might put these giant shields in the Lagrange point. And so at the end of the movie, of course, they detect this signature in test data and then start sending radio signals to them. So that's another example. And then, of course, maybe space mining might be another good case to think about.
Space mining.
So asteroid mining. So if you really want to extract all of this plutonium and gold out there, then you might imagine building infrastructure to do so. One of the consequences of space mining, asteroid mining, is that you're probably going to produce a lot of dust. So one of my colleagues, Duncan Forgan, wrote a paper about this with Martin Elvis, who's at Harvard. And they calculated that any kind of space mining activity is likely to produce a huge amount of debris as a byproduct. I mean, of course, anyone who's worked in a mine knows that. There's a huge amount of dust, and it's very bad for your lungs, of course. And so you'd expect the same thing in a solar system. So you'd have solar systems which have an overabundance of dust localized to these belts. And that could be a good signature for some kind of mining activity happening.
I'm smiling, almost giddy, just because I'm thinking about how fun it must be as an astronomer or astrophysicist to write these very rigorous scientific papers about how you would detect space mining aliens. And it's interesting. It's super interesting, and real scientific thought and rigor is going into it. And you've mentioned some papers that you've written that have been published in academic journals where the focus has been intelligent life or aliens. And I'm wondering if there are any other fun ones or interesting ones that we haven't touched on yet that you've written or been a part of.
Yeah. One of the technosignature I propose is something called a quasite, which is a type of orbit which is essentially impossible naturally. So normally, any planet or object that orbits around the sun or a planet will follow Kepler's laws of motion, which essentially tells you the speed at which the object is going to go around in its orbit, given its distance away from that object and given the mass of the central mass that it's going around. So We often talk about things being on a Keplerian orbit, or sometimes you'll see sub-Keplerian orbits, which means there's often like dust in the way, which is like a drag force slowing things down. That can sometimes happen if you have like aero drag or something for a satellite as it comes down to Earth's orbit. So what a quasite is this kind of fun idea of using radiation pressure. Maybe it's easy to start with the idea of a statite, which is something that Ron Forward proposed in the 90s. A statite is a very thin solar sail. So imagine like a piece of aluminum foil, very, very thin. And it has a radiation pressure from the sun pushing it outwards, but it also has a gravitational pressure pushing it in towards the sun. And so a statite balances those two forces. So the radiation pressure out equals the gravitational force in. So it doesn't move, it just sits there in inertial space. It doesn't orbit, which is very weird. Like normally, if you're not orbiting, you would just fall into the star. So this thing just sits there. So that would be very odd. If you saw a statite, that would certainly be very peculiar and a clear technosignature, because there's definitely no natural things which are engineered so thin and shiny that they could just hang out in space like that. And a quasite is in between those two. So a quasite is something which the radiation pressure is significant, but it's not enough to totally balance out the gravitational force. So all things being equal, it would want to fall into the sun. So in order to stop it falling into the sun, you give it a little push, so it's in an orbit. But that orbit does not follow Kepler's laws. It will orbit slower than it should. So it's in kind of like a slow motion orbit. So that would be very artificial to have such a slow motion orbit. That's useful because if you think about Mercury, which is close to the sun, the closer you are to the sun, the faster you orbit. So Mercury overtakes us many times as we go around the sun. It's going around much faster. But if you could manipulate its orbit using this quasite technology, you could cause it to co-orbit around the sun at the same speed that the Earth does. And so I propose that could be really useful for space weathering monitoring. So one of the big concerns with our technology is something like a Carrington event, which happened in the 19th century, where there was a giant mass coronal ejection event, which produced basically an EMP on the Earth, which basically knocked out all of our electronics. And so this could happen again anytime, and we have really no defense against it. And it would basically just blitz out everything in this room and across the entire planet electronically. So one possible defense against that is something called a Rutherford cage, where you can basically, some people have Rutherford wallets and things to, worry about kind of Wi-Fi leakage and NFC technology. So you can protect stuff, but really you're not going to have your stuff protected all the time. So that you want some forewarning. So you could have this quasite thing that lives at maybe Mercury's orbit. It detects the coronal mass ejection, gives you the forewarning, sends a signal at the speed of light, which will outpace the speed of the coronal mass ejection by several minutes. And so you'll probably have about a 5-minute warning to get all of your stuff that you care about into a Rutherford box as fast as possible. So that was just one idea as to how this thing could be useful. And, I can imagine a civilization potentially wanting to do space weather monitoring, and that would be a very clear, weird thing we could detect in our data.
I mean, that would be hugely helpful for national security, because if I'm not mistaken, I've read, what if the United States gets knocked out, but China doesn't, or something like that, and when we just have no defenses for some period of time.
So you won't be able to get all your technology in, but you can maybe get some critical technology protected in that 5-minute window. Mm-hmm.
And I noticed that right now, I hadn't noticed this yet, but you're wearing a very cool
Worlds
hoodie. Yeah. And how much of the research going on in your lab is devoted to questions like this?
A small fraction, I have to say, is a small fraction. And mostly it's in my team, I have a bunch of graduate students and undergraduates who work for me, and it's pretty rare that I ask them to work on these things. If they're interested in working on these things, I'm very happy to. There's one student in my team right now who's doing so. We're working on this idea of star lifting, of basically making stars live forever, or maybe not forever, but a very, very long time, by scooping material off the surface and sort of reducing the gravitational pressure. And that lets the star essentially live for longer when you do this. So how could I said the Earth will become uninhabitable in 1 billion years, but it doesn't have to be. We can actually engineer the sun to not do that. So we're developing this idea.
Is that something that you would pitch to Elon Musk?
Yeah, I don't know. It seems a little bit difficult to imagine it happening in the near future, but we have 1 billion years to play with, so I can imagine this being something which could be doable. So we're really thinking about if someone else was doing this, could we again see it? Could we notice them star lifting their star and detecting it from afar?
Super fascinating. I mean, I just am already thinking about the controversies around geoengineering when you add solar engineering, stellar engineering. Yeah, wow.
Helioengineering. Yeah. So, I mean, that's an example, but I'd say the most of our scientific work is on looking for exoplanets, exomoons.
Mm-hmm. I'm curious, though, with regard to the stellar lifting.
Yeah, star lifting.
Your contribution that you and your graduate student are working on is developing a technosignature so you could detect whether another civilization is doing this, or you're just interested in the engineering of this process, how it might work.
Yeah, so we've done 2 projects on it. The first one's already been published and the second one's in the works. The star lifting idea already existed in science fiction and literature before, I think, but it hadn't really been fleshed out. So the first paper, we actually took real astrophysical models of a star and we did the activity of removing material from its surface and really calculated how that would affect the actual evolution of the star in terms of the detailed physics, what happens in that side of that thing. So it wasn't just a speculation of, maybe the star will last longer if this happens. We actually, really ran the simulation to see what would happen if you did this. And we were able to calculate the ultimate lifetimes of these stars at different rates of removing material from the star. So one of our favorite calculations there was to remove material at just the right rate that you keep the sun the same luminosity. So the sun will grow more luminous over time as it ages, but if you remove material at just the right rate, you can basically keep it as a perfect light bulb so it doesn't change, which is ideal for us. And the rate was about 1 Vesta asteroid per year of material. So it's not even that much you have to remove from the surface. 1 large asteroid worth of material off the surface of the sun. And
now it's seeming easy.
Yeah, and you can actually do it with lasers as well. You don't even have to actually physically scoop material off the surface. You can just excite the sun's already losing mass anyway through these coronal mass ejections. So you could basically excite one part of the sun, maybe the north and south pole, and it can just eject material itself. You just need to give it a little kick to do it with lasers. So that was our first paper. And the second one, we've been really investigating the technosignature aspect. Like if another civilization was doing this, how could we detect it? How could we distinguish it from just a natural star? Are there any ways that it could trick us? So we think we have a pretty clear signature, but we've not published that work yet, and that's still in the works. But that's a typical way science works is that there's an initial idea or discussion of something, maybe in science fiction or in the literature. Somebody needs to come along and like really flesh it out and figure out, is this sensible or not? And then once you've fleshed it out, maybe if it still survives, you do the next calculation, which is, okay, what do we look for then? And then once you've done that, maybe the next step is you actually do a search. So that might be a paper 3 in this sequence. So typically you take it in baby steps. You don't rush right to the end if you don't know if it's even sensible to ask the question in the first place.
Another question about your lab and the work that you do as an exoplanetary researcher. First, though, am I right that the Clark Belt is a generic term, so not just for the Earth, but for any planet where things in orbit around that planet are in a geostationary orbit?
Correct.
That's the Clark Belt around a planet? Okay. And you mentioned much earlier in the conversation that exoplanetary research and detection is still very much a nascent science. And it's only been recently that we could actually detect that there were exoplanets in the first place.
Yeah, about 3 decades.
Yeah. So this makes me wonder how it is. Do we even have the technology that we could detect what's going on in the Clark Belt of an exoplanet?
Yeah, I mean, the way people imagine this working would be using this technique that we generally use to find planets as well, and that's called the transit method. There's several different ways of finding planets, but I think the easiest one to understand and actually the most successful method is transits, and that's when a planet passes in front of its star, it blocks out some starlight. So the appeal of this is that you don't have to actually spatially resolve the planet from the star. That's very difficult because obviously if they're many, many light years away from you, the separation between the planet and the star is so small on the sky that you just can't distinguish them. But if the planet passes in front of the star, that doesn't matter because it's going to make the star just appear dimmer for a short amount of time. So all you have to measure is the brightness of the star over time. That's called photometry. So if there's a ring system around the planet, then you might expect to detect that as well. You would get imagine the planet with its ring. The ring's going to come in front of the star first. So you get an initial small dip in light as the ring system comes in front of the star. And then you'll get the bulk of the planet comes. So you get one large dip, and then it will exit, and then the ring comes out on the other side. So you get sort of one giant dip in the middle, and then this kind of shallow dips either side, which should be symmetrical if it's a true ring system. And so we can look for that in our data. In fact, we are looking for that. We have James Webb data that we're analyzing right now on my team of a Jupiter-like exoplanet, and we're using that to look for, primarily to look for exomoons, but also to measure what we call the ablateness of the planet, like whether it's wider than it is at its equator than it is at its poles, which Jupiter and Saturn certainly are ablate. And we could look for a ring system around that thing as well. So we could use that same technique to look for these exo rings. And if the exo ring happened to be at the Clark distance location, that would be very suspicious, I think. Certainly a Jupiter-like planet, we wouldn't expect to have a Clark belt, but we could obviously repeat this experiment for Earth-like planets.
And exorings and exomoons are just rings and moons around exoplanets?
Correct, yeah.
Okay, that makes sense.
Yes.
That naming convention
Really, we should say
sense.
endo-rings and endo-planets in the solar system. Exo means outside of the solar system. Endo means inside. So I always say, Jupiter is an endoplanet, Earth is an endoplanet, but nobody else calls it that.
Mm-hmm. And I noticed in looking at the research that your lab is doing that you have a particularly strong focus on exomoons.
Yeah.
You should correct me if I'm wrong there, but I have two questions about that. One, is there a particular reason that understanding exomoons is just important for furthering our general astronomical knowledge? And the second question is, are exomoons or maybe moons just more generally a particularly interesting place to be looking for life?
Yeah, I think I can answer those together, in fact. So I normally say there's 4 really big reasons why we should be looking for exomoons. The first one is that second part of your question, that they could themselves be habitable. And we're familiar with that from science fiction, of course. You have Star Wars often has habitable moons. You have Pandora from Avatar plays with this idea most famously. So,
is Pandora a moon in Avatar?
Yeah.
Oh,
yeah.
I didn't know that.
Yeah. If you watch the opening sequence, there's this beautiful blue Neptune-like gas giant, and then the moon, this Earth-like moon, which orbits around it.
That's cool.
So I use that footage a lot when I'm talking about exomoons because it's a great stock footage for me to show. So yeah, it's certainly possible. There's no reason why moons couldn't be habitable. And it's a really important question because one of the overarching goals of NASA is to measure the occurrence rate of Earth-like planets. Now, they say planets, but I think it should just be worlds, Earth-like worlds. And it very well may be that there are more Earth-like moons than there are Earth-like planets right now because there's a lot of gas giants in the habitable zone. We know of about 1 to 2% of stars, sun-like stars, seem to have evidence for Earth-like planets around them. It's quite a small fraction. With a huge error bar, there's a lot of discussion about what that true number is. But we have much more certainty about gas giants, and they seem to be quite common. Around sort of 10% of sun-like stars seem to have Neptunes or Jupiters in the habitable zones of their stars. So an obvious question is whether those planets have moons, because then they're just the right distance for life. So that's a very exciting possibility. The other reason to do this science is we think moons have a big influence on planets themselves. So obviously the Earth is the great example here. We have a very large moon, a kind of freakishly large moon compared to other planets in the solar system. And that actually stabilizes the obliquity of our planet, the spin axis. So Earth has about a 23-degree tilt. And if the moon was not there, Jupiter's gravity would take over and cause it to wander over millions of years. And that's actually what happens to Mars. On Mars, its orbital axis actually drifts over many billions of years. So there could be periods where the North Pole is basically pointing at the sun for like 3 months of the year or something. And that would be disastrous for the climate. I mean, you could imagine simple life being fine with this, but you wouldn't be able to have agriculture. You wouldn't be able to have the kind of civilization, the agrarian civilization we have on such a world. So that seems to be an important part of our own history. So I think when we find an Earth twin, one of the first questions you might ask is, does it have a moon twin? Because that seems to have an enormous impact on our own planet. A third reason to do this is to try and understand the uniqueness of our own moon formation mechanisms that we see in the solar system. Again, with our own moon, it seems to have formed via a giant impact. And it seems like that's the only instantiation of that in the solar system, of forming such a large moon. And we just don't know how common that is. Maybe we are a 1 in a trillion event in the universe where that happened. And that's why we're here, because it happened. Or maybe giant impacts happen all the time in other solar systems, and they often form moons this way. So the story of uniqueness, I think, is one of the most interesting questions in science, is like, how special or normal are we in the landscape of possibilities in the universe? And the fourth big reason I'd say to do this science is actually more of a practical point. We want to one day build a telescope. It's probably going to be the next successor to James Webb, that will take a photo of another Earth-like planet. It will really image it. So to do that is very difficult. You have to block out the starlight with these coronagraphs, which is a very precise technology. You have to suppress the starlight by a factor of 1 billion to 1. It's a very difficult suppression. But if you can do that, you can just have the pale blue dot of the Earth-like planet. And obviously, we've done that for the Earth with our spacecraft. There's the famous pale blue dot image that Voyager 1, I think it was, took of the Earth in the 1990s at the request of Carl Sagan. So it's a really beautiful image if you've never seen that one before. And we want to capture that same image of an exoplanet one day. But as beautiful as that image will be, and it will reveal to us the gases, the composition, the surface properties of that planet, the moon will be photobombing that image, because the moon is so close to the planet that it will not be distinguishable. It will be not really a pale blue dot, but really a pale blue-gray dot. It'll be kind of smudged together, the two worlds. And so when you think you're seeing just the planet by itself, you're not. You're seeing a combination. And that could be really problematic. Titan, for instance, has a methane-rich atmosphere, and the Earth has oxygen in it. And you can imagine that oxygen being produced without life. Actually, there are ways to make oxygen just through ultraviolet radiation breaking water apart, for instance. So if you had that combination of a lifeless Earth that had oxygen from this ultraviolet radiation, and then you had a Titan-like moon that was photobombing inside there, you'd have methane and oxygen. And you would think that is actually the classic biosignature. That's what astrobiologists talk about as being the dead giveaway that you found life. If you have those two things together, that's chemically impossible to happen unless there is life active on the surface. That's what they say.
Smoking gun.
The smoking gun, thank you. And so this moon would trick you. You know, if you didn't know that moon was there, you would erroneously conclude that you detected life. So just from a practical perspective, we are not going to be able to do that experiment. We just cannot do that experiment until we know how often moons get in the way. So for me, that's a really big reason to do it as well.
Well, the first thing I have to note is obliquity is a wonderful word that I've never heard before.
Okay.
So thanks for enlightening me. The next thing of interest is you distinguished between planets and worlds, and it reminded me of a conversation I had with Konstantin Batygin.
Oh yeah, friend of mine, yeah.
Yes. And I think I also spoke with somebody named Alan Stern.
Yeah.
So they are kind of in argument, debate about whether Pluto is planet 9 or there is some other planet 9. And we don't need to get into this minutia, but there's questions of how a planet should be defined. But something I learned in these conversations was that we should expect there to be an abundance of planet-like objects traveling in the interstellar medium that aren't tethered to one star or another. And it just occurs to me now to ask whether or not these are places we might expect life to be, even if we don't really have a way of detecting these planets the way we might those around a star.
Yeah, I think actually we could detect them, and we have evidence for them already in our observations. Maybe the life forms themselves, unless they were Kardashev scale, would be more difficult. But we can, maybe just to tie that knot though, we can detect them through a different effect called gravitational microlensing. So planets have mass, and so if they're a free-floating rogue planet drifting between the stars, they will sometimes not exactly obscure a background star, but come close to obscuring it. And then the light can be lensed, bent around gravitationally that planet and cause a focusing event. And so we can actually detect these brightenings that happen due to this gravitational lensing effect. So just using Einstein's theory of general relativity, essentially. So we detected thousands of stars that do this, just stars that pass nearby other stars. We've detected dozens of planets around those stars using this method. And there's even some evidence for free-floating planets using this method as well. And there's an upcoming telescope called Roman that will hopefully detect hundreds of free-floating planets. So we're really excited about that because it's going to really break ice as to what's really going on with these free-floating things. Now, to turn to the question of life on those worlds, there was a paper, I forget the author, but he called them Wolfenstein worlds. I'm not sure why. I think it was like some story in science fiction, I suspect, that played with this idea that he was borrowing the name from. But it was actually using moons to create a habitable environment. So Io is too far from the sun to have, to be warm on its surface due to solar radiation, but it still has pockets of warmth because of volcanism. Now, that volcanism is not being induced by the moon itself. It's being induced by its gravitational interaction with the other moons and Jupiter. So it's tidal flexing happening inside that moon. So it's a completely different source of energy from all the source of energy that we use here on the Earth for life. So it is possible that even though you don't have a star, you could still have that source of energy to produce a biosphere. Maybe not a biosphere as rich and fully developed as our own, but you could certainly imagine some simple life around these kind of thermal vents clinging on and developing over billions of years.
No, that's very interesting. When you think about the crazy places you find life on Earth around.
I mean, it may be that life is everywhere. I mean, certainly if you go into your bathroom, you find life everywhere.
Yeah.
And maybe...
Hopefully not too much in the bathroom.
Right.
But yeah, and then one other thing I wanted to follow up on is you mentioned this next generation of telescope. And I think most people who aren't up to date on the science, when they hear, oh, an exoplanet was discovered or detected, they don't realize how indirect the methods currently used are relative to just seeing it. And I think that maybe I listened to an episode on Sean Carroll's show a long time ago about this, but a future telescope being built on the moon that can just be so much larger than something that we might put into orbit. And I'm wondering, is this successor to the James Webb a moon-based telescope or an orbital telescope?
It's not on the moon, it's an orbital telescope. It's currently, the moniker is the Habitable Worlds Observatory, HWO. It'll probably get rebranded at some point because telescopes usually do get named after someone at some point. I suspect Carl Sagan might be the obvious person to name after. So we might imagine this Sagan telescope being built in the late 2030s, early 2040s, or being launched at that time. So it's a long way off. And it's expensive to do this stuff, right? I mean, James Webb was $10 billion. And this telescope will be probably more expensive than that.
Was that government money? Because now that's in a lot of question.
Money. Yeah, that's taxpayer money. It was originally supposed to cost, I think, $800 million at the very first version that they imagined. And then it went up to like 1.2, then 2, then 3, then 4. And it just kept rising and rising. I think they did have a problem with their contractors, but there was also almost certainly an underestimation of the complexity of building this thing as well. So I think there was both budgeting, over optimism with the initial budget and issues with the contractor that led to this kind of ballooning of the costs. But I think NASA says that we've learned the lessons from this. This won't happen again. But obviously, it's not the only case where that has happened. So the Hubble Space Telescope also was obviously quite a lot over budget. When it launched, the mirror was out of focus, and it cost another, I think, $1.2 billion to send astronauts up and repair it. So I think we just have to accept that, doing high fly technology that's pushing the very limits of our capabilities is always going to be an expensive endeavor. I mean, you're talking LHC, the Large Hadron Collider was, again, like that sort of level, like $10 billion, $13 billion. So I think we have to expect it to cost a lot of money. I think the concern I have for that is, when JWST was eating up all of this money at the time, it was actually very bad for a lot of other astronomers because NASA couldn't do anything else. It only has a fixed budget, and it was using almost all of its science budget to develop JWST, which meant there was less money for doing other missions or other types of science. And so that did have an impact on the community, that there was less grant money, there was less innovation in other areas until JWST got in the air. And then we all kind of had a big sigh of relief that JWST, A, was successful, but B, that it was just out of the way, because now it freed up funds to do other innovations. And so a big, kind of looming dragon, I suppose, ahead of us with this next successor is this going to eat up the whole budget till 2040 for many, many years to come? That would be, concerning. And I think we should ask reasonably, there is obviously a focus on efficiency at the moment in this country. Are there more efficient, cheaper ways of trying to get to this goal? And maybe, you mentioned a telescope on the moon. That's actually one possibility people have floated, is maybe we don't have to have an orbiting spacecraft to do this. There's certain reasons why if you actually already had a lunar base, it could be perhaps more affordable to do something like that. I've written about an idea called the terrascope before, which is actually not even really building a giant telescope, but using the Earth as the telescope. The Earth lenses light naturally through the atmosphere. So this is not gravitational lensing, which you might initially think of, because the Earth's gravity is far too weak for that. But it does lens light through refraction, which is just, the bending of light through the atmosphere. Especially if you look at a sunset, just as it's dipping below the horizon, it looks like it's on the horizon, but it's actually already half a degree lower than that. And what's happened is the light has followed a curve to your eye, and your brain interprets it, of course, as a straight line. So you get about a half a degree bend. So light from the sun goes half a degree and then another half a degree on the way out. So it's a 1 degree bend. And if you calculate where it comes to a focus, it's actually not too far off the distance of the moon. So there's probably the best point would be a little bit further out than the moon, but you could potentially put a small telescope out at that distance that would have the collecting area of about, the amplification is around 40,000. So you can get a huge amplification just using the Earth as your lens. So I'm not suggesting we should do this instead of HWI. I want to be very clear that that's not my suggestion, because this is very much a pie in the sky, underdeveloped idea at this point. But I do think it's worth asking about the other innovations which are in our community, about thinking about ways to do this in an affordable manner, because of course this is a lot of money for the taxpayer and they want to get their most bang for their buck. And I'm certainly cognizant of that as a US taxpayer. I want to make sure my money goes to doing things right. But I think we also have to accept that if we want to be, the world leader in whatever science it is, then that requires investment. And NASA's budget is actually very small. A lot of people think NASA's budget is like 7-8% of GDP. Typically when you ask people and you poll them, that's what the median answer they give. But it's actually less than 0.5%. It's a tiny, tiny fraction of the US budget. And the science budget is a tiny fraction of that. That NASA budget funds all of the aerospace and rockets and contracting SpaceX and all that kind of stuff, the human spaceflight program, and then the actual science aspect that funds James Webb and all these telescopes is a minuscule fraction of that. So it's not a lot of money that we put into this. And Neil Tyson often likes to say this. I think it's a nice saying, like, what is the cost of the universe? Like, how much are you willing to spend on the universe? So if you doubled that budget from 0.5% to 1%, we wouldn't be talking about 2040s. We'd be able to do this like in the next probably 5-6 years. So, it's just, we are very much constrained by a limited budget in making these dreams happen.
This price tag would probably be a lot more appealing to people if you could tell them that the resolution would be sufficient to detect certain alien megastructures, possibly. Is that conceivable?
Yeah, I think it is. Obviously, you have to be careful with not overselling your missions. Mm-hmm. Obviously, even the name Habitable Worlds Observatory implies a specific science goal, right? It implies that this mission will detect a habitable world and take a photo of it. But we don't know for sure that it will. Maybe there are just very few Earth-like planets out there. We still don't really know the occurrence rate of Earth-like planets around sun-like stars. So it is quite possible that it won't detect any. So we do have to be careful with not promising something that, yes, it's capable of, but just doesn't exist in the universe. So if I say to you, it's going to detect megastructures, People might get very excited about that, but what if there's no megastructures to detect? Then it's just not going to be able to achieve that goal. So I do think we have to be candid and honest. That's why I like doing these podcasts. That's why I like talking about cool worlds, is to try and build a level of trust and transparency with the public about what is realistically possible and not possible, and just to set the clear intention that we want the same thing as you. We really want to detect aliens out there, but I don't want to promise you something that is not out there because we don't know yet.
Talking about what's possible and not possible, I want to go back to star lifting for a moment. And just to briefly mention it, star lifting seems like it would be useful, as you said, because it might be a way to stellar engineer to prevent the Earth from being destroyed.
Cooked, basically, yeah.
Yes.
Yeah.
And this is something that, I mean, Elon Musk says that we need to expand past the Earth to avoid possible existential threats. And another video, and this is where I'm getting to what's possible and what's not possible, on the Cool Worlds Lab YouTube channel, is what's stopping us from building a warp drive? Mm-hmm. And the first question is, what specifically or exactly is a warp drive? Because I'm sure in different science fiction stories, it means different things.
Yeah, it's like the hyperdrive in Star Wars. And the warp drive. Yeah, so this is, I think most when scientists talk about warp drives, we think of what's called the Alcubierre drive, named after Miguel Alcubierre. And he was actually, like me, he grew up on Star Trek and was inspired by it. And so he asked himself, is there a solution within Einstein's field equations to do something like this? Does general relativity allow, in principle, a device which could travel faster than the speed of light? It's kind of a trick because the spacecraft itself doesn't move in its local inertial frame faster than the speed of light. It's moving certainly subliminally, but really the trick is that you kind of bend space around you to create almost the illusion from the outside that the spacecraft is moving faster than the speed of light. So the observers do not experience extreme time dilation or anything like this, which is a nice benefit. Obviously, if spacecraft were traveling very close to the speed of light, clocks would all get way out of sync with each other, and that kind of messes with your perception of space travel quite a bit. So the Alcubierre drive is a actually legitimate solution as to how you could do this, but it's really reverse engineering. I mean, he really started from the position of let's assume such a thing is possible to build. Is there a solution within the mathematics to make this happen? But it's not obvious that it is possible to build something. So one of the consequences is that you need something called negative energy, for instance, to make these distortions to space-time. And we certainly don't know of a significant source of negative mass or negative energy in the universe that we could use to this effect. There's very minuscule negative energy experiments like the Casimir effect, which have been demonstrated, because you get two plates very close together and you kind of get like a negative pressure between them. But it's such a negligible amount of force that this is, beyond imagination of what Alcubierre is talking about. You also need these incredibly dense shells made of basically like neutronium. Neutronium is the stuff that neutron stars are made out of, so extremely dense exotic matter.
It's like a teaspoon of that would...
weigh the Mount Everest type level. Yeah, so you need a huge amount of mass. The actual energy requirement to do this is calculated to be gigantic. Some calculations put it sort of the level of turning Jupiter into pure energy via equals mc squared.
That's why you need to be a type 2 civilization.
Right, probably even more than that. So yeah, there's lots of these constraints, but those are all really what you might call engineering problems. Albeit engineering problems which are way, way ahead of anything we can imagine solving in the near future. But there's also a bigger problem, which is that Alcubierre himself concedes this in his paper, that any faster-than-light system, if you work through the math in general relativity, it allows for what's called a closed time curve, which means reverse time travel. So you could basically have grandfather paradoxes type situation where you can go back in time and kill your own granddad and then you shouldn't exist. So what does the universe do in that situation? Are you there or are you not there? And Stephen Hawking really hated the possibility of reverse time travel. And he has a conjecture, it's not proven, but he has a conjecture that that's just forbidden because causality violations would make the universe essentially an illogical place. And as far as he could determine, the universe is strictly governed by logical sets of rules. So he really didn't like that idea, and he conjectured it was impossible. And if it really is impossible, then it means there's something about warp drives that is not possible. Like, no matter how hard you try to build one, maybe you construct one, but as soon as you turn it on, it kind of destroys itself or something. Like, there's some kind of feedback which prevents it. A good example is like wormholes. Like, if you take a wormhole and you have the two mouths, they can potentially create a time travel machine as well. Even if you make the two openings of the wormhole at the same moment in time, you could always put one on a spacecraft accelerated at high speed, then coming back, and that time dilation would cause them to be out of sync. So now you have a time travel machine. But there's several papers which show that you get feedbacks between these. So you could have a particle like a photon, which enters one hole and goes backwards in time, and then it could come back and loop back around. So there'll always be at least, one particle path or one field line, even not even a particle path, a virtual particle, which will do this. And as it goes round and round and round at any one location, you're going to suddenly double, triple, quadruple the energy density at that point as this thing loops round and round and round. And in fact, that will happen instantaneously if you think about it, because it's time traveling. So the amount of energy density at the two openings explodes to infinity, and the thing destabilizes instantaneously. So it's the same kind of effect of putting like a microphone to a loudspeaker. You get that like huge feedback effect, and the two wormholes, if they're out of sync in time, would create the same effect of basically destabilizing themselves instantaneously. So it's thought that whenever you like come up with a solution like this, like wormholes or warp drives, whatever it is, the universe will always find a way to basically destroy that thing that you've just created. And it's not by it's not because there's some god who's like making sure that doesn't happen. It's just because if we lived in a universe where that was possible, the universe basically would have eliminated itself. It would be a completely unstable, chaotic place, and none of us would be here.
That's very fascinating way of answering the question, what's stopping us?
So I think that is the biggest thing that's stopping us is if these machines are capable of reverse time travel, which seems to be the case, and if reverse time travel is prohibited, then that's basically a hard stop in terms of the laws of physics, and everything else is very strong engineering problems along the way. So my own bet is that's not possible. Of course, with the reverse time travel as well, you could also have not only people visit, aliens could not only, it makes the Fermi paradox so much worse, because not only do you have to explain why we don't see aliens, sending radio signatures to us within our local galaxy, you now have to explain why we don't see ships with warp drives entering our system from not just our universe, but the infinite universe, right? Because a warp drive can travel across the universe potentially at any time it wants. So now you have, if the universe really is infinite, you have an infinity problem to deal with. Like, there should be infinite numbers of warp drives in our solar system right now as a result of this. And not only in space, but also in time. Because of the reverse time issue, ships from the future could also come back and visit us at this point in time. So it really makes the Fermi paradox almost untenable, I think, if you allow for warp drives.
Do you know the name Gary Nolan?
To do with UAPs?
Yes.
Yeah.
Yes. He's a med school professor at Stanford, highly renowned in his field of immunology and cancer biology. Also a UAP researcher. I interviewed him. His episode on aliens will come out before this one. Mm-hmm. And he says that for a long time, he thought that aliens were time-traveling humans from the future who were coming back and interested in observing us. And the reason that I bring this up is that initially one might think that time travel and aliens are different questions, but evidently they can be put together. And so obviously your focus in your research is on exoplanets, and then intelligent life becomes part of that. Do you have also an interest in the feasibility of time travel just as a physicist, or?
I do. I think it's mostly come about through the work on YouTube and public communication. Actually, I had a Grant Lewis, who's a colleague of mine. He's a cosmologist. And I don't know if you know the Veritasium channel. Derek Muller is a really popular science communicator. And I got to know Grant Lewis a little bit through his videos because he often pops up in Veritasen's videos. And then I realized he's a cosmologist who's actually also very active in a large number of topics. But he got interested in this question of time travel as well. So he was actually visiting me yesterday, and we probably spoke. We were by the whiteboard working this all out for about 2 hours, working at sort of space-time diagrams, trying to figure out whether this is sensible or not. There's sort of this argument that within general relativity, reverse time travel is allowed or not allowed. And so I think there's still a lot intellectually to be done there. I'm by no means an expert in that topic, but I guess it's a little bit like the giggle factor aspect. There's not a huge amount of research done on this topic because people think it's a little bit kind of silly and facetious almost. But I think through my work as a science communicator, I appreciate this is a thing that people really care about and are interested in. And why not? It's a totally legitimate and interesting question, a very profound question to ask. And obviously it connects back to my research, as you say, about intelligent life in the universe as well. So I've kind of got interested in it almost obliquely through that connection of the science communication. And I do think being a science communicator has made me a better scientist in that respect. You know, I used to only focus on moons and planets, and that was it. That was my whole universe, was just thinking about that. But as I've become more and more adept at talking about different topics in cosmology, black holes, time travel, these kind of topics, the size of the universe, it has forced me to become more well-read, grow my expertise, and find connections between different disparate topics that I didn't realize were interconnected to each other. And I think that's made me a better researcher as well. So it's a really fulfilling activity, actually, to do that.
Are there candidates that, unlike the warp drive, which does not seem, well, it seems like it could be very much not just technologically, but perhaps even theoretically not feasible. Are there candidate time machines that you find more plausible or appealing than others for various reasons?
Well, certainly time travel to the future is easy. That's the first thing to say. So, you know, we say time travel, I think you probably mean reverse time travel implicitly there. But obviously, going forward in time is not a problem whatsoever, and special relativity makes that very clear.
Forward by skipping the intervening time in some way.
Yeah, you can't skip, but you can accelerate the rate pretty extremely by traveling close to the speed of light. So that's your time dilation factor in special relativity. So I have a video called, one of my most popular videos called Journey to the End of the Universe, where we play with that idea and show how in a human lifetime you could actually visit essentially the end of the universe in terms of the heat death of the universe by just constantly accelerating at 1G for about 100 years or so.
Really?
Yeah, it's kind of remarkable how that compounds. You know, compound interest is the most awesome force in the universe, I think, to paraphrase Albert Einstein. And so in the same sense, if you keep accelerating and getting closer and closer to the speed of light, this time dilation factor gets really extreme. And you could literally visit beyond the end of stars and galaxies and black holes into this heat death era just by, in a human lifetime of acceleration of 1G. So pretty terrifying how easy it is to do that, actually. There's no reason why physics prohibits that. But reverse time travel, I think, is the thing most of us are more interested in. And that really seems very difficult to imagine away. I think wormholes and the Alcubierre drive are the most commonly invoked ideas to try and do this. Neither of them obviously have been practically demonstrated or proven. We don't see any evidence for naturally occurring wormholes in the universe or anything like this. But in principle, you could maybe engineer one, but there's these issues with how stable such a thing would truly be. So my big hunch is that it's just prohibited, and that probably is for our own well-being, to be honest, because we would probably almost certainly screw up our own timeline if we were capable of doing such a thing.
Speaking of all of these technologies, warp drives, time machines, there was another video I wanted to talk about, which is interstellar propulsion technologies ranked. And I'm wondering what the options are that we can choose from, and then how you're going to be ranking them.
Yeah, that was trying to focus on sort of things which we might really imagine being possible in our lifetimes. So I did put warp drives on there, but I gave it a pretty low rank just because it's not something I think I'm going to see in my lifetime. I think we're all kind of selfish like that. Like we want to actually see something where we have a chance of witnessing it in our own existence. So wormholes, I think I put on there as well, but again, I gave it a pretty low rank. So most of the technologies were focused on sort of pushing the very limits of engineering of what we can do with current technology. So nuclear pulse propulsion, I think, was pretty high at the top. I think I gave that either an A or a B grade, if I remember correctly. And this is the idea of essentially detonating nuclear bombs behind the spacecraft and using the energy of that explosion to propel the spacecraft forward. It was actually explored in Three Body Problem. I think it's the first science fiction, the Netflix show, depicted it. I don't know if it was in the book as well, but yeah, they depicted it where they had a spacecraft that they accelerate by dropping bombs behind, and it's pushed forward. So you can get to sort of not 0.99 speed of light, but you can get to an appreciable fraction, maybe 10, 20% the speed of light by doing this.
Two questions about this one. One, how would the ship itself be shielded from the blast from the bomb? And then the second thing is, wouldn't this really sudden acceleration that would come from the detonation of a bomb like this be deadly to the human who is being accelerated?
Yeah, so the shielding, well, but that could also be deadly, of course, the actual radiation. The shielding is a big problem, and it means that you have to have a massive spacecraft. So you need a huge amount of basically lead or concrete or something at the back of the spacecraft to be that shield. And that shield's obviously taking a huge amount of damage as a result of this as well. So you need tens of meters of a very thick, strong material at the back of the spacecraft, which means the weight of this thing is huge. And that's probably the biggest practical issue, is that to actually build such a thing, you'd have to have an enormous amount of space engineering infrastructure already in place, because you couldn't build this on Earth and get it off the surface. It would just be too massive. And you certainly don't want to use nuclear bombs to lift something off the surface of the Earth. That'd be incredibly dangerous. So that's a big problem, just the amount of shielding you require. The acceleration, I don't think is as big of a problem, because the idea is to sort of almost use like micro nuclear bombs and just have a continuous stream of them. So in that sense, you can sort of dial it down to a tolerable level of acceleration. But it's probably, none of these technologies are that well suited for humanity. Probably my favorite on there is actually completely useless for humanity, and that's the idea that Breakthrough Starshot was chasing for a few years. I think they've now stopped that investigation. But there was a Russian billionaire, Yuri Milner, who lives in Silicon Valley. And he funds the Breakthrough Foundation, which funds a large number of scientific enterprises. They have the Breakthrough Prizes, which is kind of like meant to be like the Oscars, but for scientists. And they kind of have many celebrities host those, tuxedo events of giving out prizes to scientists.
The world needs more of that.
Yeah, it's really fun, actually. Yeah, so fun to tune in and watch those. One of my colleagues at Columbia recently won one, Brian Metzger, and he also funded this Starshot project. And the Starshot project was supposed to be $100 million put towards thinking of the best way we have, get the best engineers, physicists all together in one room and get them to figure out what is the most realistic way of, in 20 years, 30 years, of getting a spacecraft to Alpha Centauri. And the idea they convened upon was using laser propulsion. So you get a very light sail, like a solar sail, essentially, maybe 10 meters across is sort of the ideal size they came up with. And it will weigh hardly anything, maybe just a few grams. And then you attach to it a microchip. And that microchip is essentially the payload. That's the spacecraft, really, the microchip. So it's something you can actually hold in your hand. It'd be like this big, maybe just a few centimeters across. And on board that, you have like an iPhone chip, basically. So you have your smartphone camera, you have your GPS sensors, or really not GPS, but magnetometer sensors, accelerator sensors. All of your circuitry, your communications is all built into this one tiny wafer chip. And then you have about a 10 gigawatt laser system on the Earth, which shines, so it'd have to be a whole fleet of lasers, and they all shine an intense laser beam at this sail, which sits in orbit of the Earth, and is pushed forward in the space of a few minutes up to relativistic speeds. So the thing gets like 20% the speed of light. And then at 20% the speed of light, Alpha Centauri is 4 light years away. So you could reach that in just under 2 decades. And then it won't be able to stop. There's no stopping mechanism on this thing. So it's just going to zoom past at relativistic speeds. And it will hopefully take a photo and then beam that photo back. And the idea was actually to use the sail as the antenna. So it's kind of clever to like reuse the sail for the communication purposes. And then that would give us maybe not what we want to actually step foot on Alpha Centauri, but it would be an actual flyby mission of an exoplanet that could be achieved in a few decades. So that was the idea. There were lots of problems even with that idea that were put forward against it, such as what about interstellar dust? If you're flying through with this very light sail, even like a single particle of dust is going to puncture that sail and cause damage. And I think the resolution to that was just build lots of them, just build thousands of the damn things. Because once you've got the laser system, that's the expensive thing. The actual spacecraft itself doesn't cost that much money. So you can just build thousands of them and hopefully a few will survive and get there at the end of the day. So I thought that was the most plausible.
Yeah. Did this win the prize of $100 million?
No, there was no winning of the prize. Yuri Milner put forward, he said, I don't know how much of it he actually spent, but he said he was going to put forward $100 million of his own money for the development of this technology.
I see.
So that was already sort of committed. But I'm not sure of its current status. I think I've heard rumors that the project has now stopped, but I'm not sure officially what the line is.
Well, this light sail technology brings me to another issue. You and we mentioned Avi Loeb earlier in the discussion. I interviewed him, I don't know, a couple of years ago or so about Oumuamua. And one of the hypotheses was that Oumuamua might have been a fragment of a Dyson sphere or light sail. But for our listeners, before we get into that, for our listeners who aren't familiar with this incident, what was Oumuamua and what was the controversy around it?
I mean, it was a fascinating discovery. I think it was 2017 or 2018 it was discovered. And it was the first example of an asteroid that was detected whose orbital parameters were such that it could not be bound to the sun. It was essentially moving too fast through the solar system to possibly be a stable orbiting object, which means it was an interstellar object. So it came from another star system, which was a fascinating example of what was possible. I don't think anybody expected that. I think we knew that interstellar asteroids probably existed. And when we did our calculations as to how often we expected them to come through the solar system, it was like a factor of 100 less than what would be necessary for us to detect it. So the fact we even saw it was very surprising. It meant that there was way more of this stuff than we anticipated. And that's actually one of the reasons Avi leveraged to suggest this could be artificial, right? Because if you believe the natural rate, then this shouldn't have happened. So maybe someone sent it here deliberately or something. I think more realistically, we probably just made an error in those initial calculations, and there's just a lot more scattering that actually happens in planetary systems than we expected. It also seemed to have a pretty strange shape. So we can tell the shape by watching how much light reflects off it. So light reflects off it isn't just a constant. It obviously gradually dims as the object moves away from us. That's when we detect it. We detect it on the way out. We didn't see it on the way in. We detected it once it was already on the way out. I think it was in Pan-STARRS, and a telescope survey detected it. And by monitoring the brightness, you can see it going up and down, up and down, up and down. So it's actually spinning. And it's not clearly a sphere, because if it was a sphere and it was homogeneous, it would spin, sure, but there would be no differences in brightness. This thing had huge differences in brightness. I think it was like a 10-to-1 brightness change. So that suggested it had a very high aspect ratio. So it was either like a pancake, like almost a UFO saucer-shaped thing, or it could be like a cigar shape. Those are two possible shapes that people concluded were compatible. And neither of those are really anticipated. And again, in the solar system, there are very rare examples of asteroids which have extreme shapes like that, but they're definitely not par for the course. So it's a little bit surprising that the first interstellar asteroid would take on that shape. And then finally, the other weird anomaly about it was that it didn't seem to be decelerating at the rate it should do as it moved away from the sun. Obviously, the sun's kind of pulling it back with gravity, trying to slow it down as it leaves. but it actually seemed to be decelerating less than it should. So in other words, it was almost as if it had a little propulsion system on board that was pushing it along, but a very, very, very tiny propulsion system. It was a minuscule difference, but a significant difference. And sometimes comets and asteroids do that. It's actually been seen many times, and that's because they outgas. So as they swing past the sun, often they have lots of ice on the surface, and that ice melts and sublimates, and it forms like a gas jet. So that's like a little propulsion that powers it along. So it's not surprising that could happen. But I guess what was surprising is that we didn't see any such jet coming off it. So if it was being propulsed that way, we might expect to see the gas coming off it, but we didn't detect any gas coming off it. However, it's not impossible that there was gas coming off it, just not the gas we expected. So when you look for this gas, you have to use telescopes with a certain wavelength sensitivity, and we mostly tuned it to sort of the usual suspects of what gas could be coming off it. But there's some gases like carbon monoxide, I think, which are less commonly released from these asteroids, and we didn't check for that. So it is possible it was just a gas that we didn't expect that was being outgassed. And I think that's kind of the end of the story in terms of our observations. And so Avi stepped in and said, like, all of these anomalies maybe are consistent with it being a light sail. And I would interpret what Avi said to be that this isn't definitely a light sail, but there's just this possibility. And I think that's not an irrational thing to say. But it does kind of also suffer from the God of the gaps aspect of aliens that we talked about earlier, how aliens can explain everything. So whenever you come across something you've never seen before for the first time, like a pulsar, you've never seen such a thing, it's really tempting to say aliens did that. And it works. It's a pretty good, efficient hypothesis. But it's often the case, as we've learned historically, that our knowledge has just not yet caught up to the current state of the art. So yeah, I tend to lean on the idea that this is something else. And certainly there are other hypotheses, natural hypotheses, which kind of work. But I know Avi has issues with some of those alternatives as being somewhat implausible and contrived as well. So it's a mystery. And I think the most interesting thing about Oumuamua is that it should not be the only one. We have new telescopes coming online just this year called Vera Rubin, which should detect about 10 of these every year. So we should get lots of these things. And once we start seeing lots of them, we can really understand what's going on with the population, and we could even intercept it. So there's a European proposal to build an interceptor mission, which would just sit in the solar system waiting. And as soon as we detect one of these things, it turns its engines on, goes full blast, and tries to catch up, land on the thing, and then send images, sample the surface, do mass spectrometry, and then we will know exactly what it is. So I think that's a really exciting possibility. It will be our first, rather than landing on another planet, an exoplanet like Alpha Centauri, and taking samples of the surface, why do that when the material is coming into our solar system? We can do it kind of way cheaper. So it's an opportunity to learn what exoplanets are made out of kind of the cheapest way possible. So I think that's a very exciting prospect.
Yeah, no, that's very exciting. One question, though, that this discussion raises when coupled with the discussion we just had about possible propulsion methods is, so the most successful of the possibilities was this idea that we would have a light sail that would propel this very, very tiny object. But Oumuamua is significantly larger, and if it were just a fragment of a light sail, then presumably it would be much, much larger than that. Mm-hmm. So is a light sail a practical method, even if not technologically feasible, to propel something very large too?
It depends what you mean by large. If you mean in terms of its actual physical size, sure, it can be as large as you want it to be.
I mean massive.
Yeah, if you want mass, which I guess is what you mean, then it's not ideal at all, because really the key number is what we call the areal density. So that's the mass per unit area. And you want that number to be tiny, of order of sort of 0.1 grams per meter cubed, which is just like a few atoms thick is what we're talking about here. So if you take like aluminium or zinc or gold. Sometimes people talk about these materials as possible candidates. You need sort of like 20, 30 atoms thick of that to achieve that density. So extremely thin, and you really can't afford any extra wasted mass on that thing whatsoever. So we don't know the mass of Oumuamua. So no one measured the mass of Oumuamua, so we don't know what its true mass would be, but we know its proportions. I think it's of order of sort of 100 meters across. So there's no reason why that you couldn't have a 100-meter light sail. But I would say, there's some things about being a light sail which look a little inconsistent. The surface is not shiny. I mean, a light sail should be shiny. The surface is not particularly shiny on this thing. It looks, very degraded over time. So maybe it's once upon a time was a light sail and now is covered in dust or something. But it's also tumbling, which is kind of odd. It doesn't have any, it's certainly not an actively controlled light sail. I think we could say that with absolute certainty because the thing's just tumbling around in space. It's not pointing its sail at the sun all the time like it should be. So I'm a little bit skeptical that it truly is a light sail given those properties. But I think the exciting thing is it's a testable hypothesis, right? As I said, so we should have more of these things emerge in future surveys, and we even could land on one of these objects in the future. So whatever your opinion, the exciting thing is it's testable science, and that's science at its best.
Well, there is one other object beyond, well, maybe I shouldn't say one type of object other than Oumuamua, whose propulsion I'm very curious about, if these are in fact real objects. So with that as my prelude, I want to say, in the last few years, the alien-related event that I've found most peculiar and interesting are these Pentagon UFO videos, and I know that you've done some videos on these as well. First of all, I mean, for our listeners or viewers, if they don't remember these, what are these videos? Like, what do we actually have, and what are some of the conclusions that people have drawn from them? Not you necessarily.
Yeah, I mean, I'm certainly not an expert on UAPs. I want to be clear about that, but I did want to address it because obviously we talk about searching for alien life, and then here the whole world is talking about these videos that came out. So it seemed like we have to acknowledge it and like address what's going on the channels. That's why I felt like it was important to discuss it. But I'm definitely not a ufologist or anything like that. So the videos I think there was 3 videos that were released. They had these nicknames like Go Fast, Gimbal, and Fleur, I think were the 3 names. And they were more or less named after the instrument, I think, that was used to detect it on board the F-18s. And there's also audio commentary. And I think when you watch it with the audio, I think that's what's, so startling. I remember when I first watched it and you hear how surprised the pilots were about it, it really takes you aback because you're thinking, wow, if even these guys have never seen anything like this before, like what the hell is going on? So a lot of, I kind of defer to other experts who are studying this. And I try to, obviously as a scientist, we naturally have a very skeptical approach to addressing very sensational claims. To quote Carl Sagan, extraordinary claims require extraordinary evidence. That's sort of our bar of accepting new claims like this. And as far as I'm aware, there are credible alternatives, explanations for those particular 3 videos as to what's going on. And Mick West in particular has done a lot of work on that. And I know he's become sort of a controversial figure from the ufologists because a lot of people have been debating him about these various ideas he has for what's going on. So
is Mick West an astrophysicist? Or
no. He used to be a computer programmer, a game developer. I think he developed Tony Hawk, those games.
Oh, okay.
And then he was sort of retired, I guess, and then became a full-time debunker of these sort of like chemtrails. He did a lot of stuff on chemtrails of airplanes, and then got into the whole UFO business as well. But he's done a really, I'm not paid by anyone to do these experiments. So it does kind of require people to sacrifice their own time to try and reproduce what's going on. And he has made the effort to do that. So I applaud him for that. So I interviewed him on my channel. He gave some, I thought, fairly credible alternatives as to what might be going on. But I do want to say with the whole phenomena, I think it's really intriguing. And Avi Loeb's obviously also intrigued by this and has spoken about it extensively. And he's proposing, why don't we just try and collect more data? Because that's what science is about, it's getting more data. And at the end of the day, having these 3 videos is not very satisfying because we don't really know the details of the instrument's behavior that were used to take them. We don't have like all the sensor data that was on board those vehicles. It's not been released. We don't have like the radar data associated with it. So there's all this like extra information that we just don't have. And that's frustrating because as a scientist, you really want to look at the ensemble of evidence and try to reconstruct like the path of the object, its altitude, or its motion, all these kind of properties. And it's very difficult to do that with just audio commentary and a grainy video. So I think the spirit of trying to get more information is wonderful. In fact, there was a NASA task force that was commissioned to investigate not just these videos, but the whole UAP phenomenon in general. And it was led by David Spergel, who's a renowned cosmologist and a colleague of mine. And I chatted to him on my podcast about his work there. So he led this NASA UAP task force to investigate what was going on. And that was their conclusion. Their conclusion was that something like 99% of the reported cases have natural alternative explanations that we can think of that would explain what's going on. There's a small fraction, roughly around 1% or so, that they can't explain. But that doesn't mean it's aliens. Just because you can't explain it doesn't mean it's aliens. It just means the data is not really sufficient either way at this point. But it's possible it's aliens. They can't exclude that. And really what's missing is more high-fidelity data in those cases. And so they advocated for a program that maybe NASA could lead to try and collect more information about what's happening in our airspace. And actually, David Spergel was a big fan of trying to develop like an app for iPhones, for instance, because we all have these very sensitive sensors on our cameras, but also the magnetometers, the accelerators, the GPS sensors, all of that information. If someone sees a UFO, they could image it and the app could collect all that information. If there's hundreds of observers seeing the same thing, you could then 3D reconstruct the path of that object and get very detailed information about it. And so that would be like a big step forward, right? Is just to have that kind of high fidelity program to really track what's going on. So yeah, my opinion is we just need better quality data than what we've seen so far.
What were because I also find this very perplexing, what were some of the alternatives to aliens that Mick West suggested that you found plausible?
So I think the trying to remember which one it was. There was one where it was like the object was rotating, so it looked like kind of like a UFO that was kind of rotating around in the background. And I think in that case, the hypothesis was that there was the back engine, the back of a jet engine, essentially, that you were looking at, and that the rotation. I think he was able to, in my opinion, fairly convincingly demonstrate was consistent with just the gimbal on board not the spacecraft, the aircraft rotating, and then it kind of hits like a certain lock point, then it re-rotates back round. So it kind of creates this mirage that the thing is rotating, where it's actually just the gimbal inside the camera actually rotating. So yeah, I really direct you to Mick West for the details on that, because it's been a long time since I looked into that in any detail. But I found that explanation fairly convincing. And certainly there's precedent. He pointed out there is precedent in, like, for instance, in Chile, there was a claim of a UFO under similar circumstances of a leaked military camera of what seemed to be a claimed UFO moving very fast. And then Mick was actually able to demonstrate using, I think, ForeFlight, one of these apps where you can get the location of all aircraft. It was the exact path of a commercial aircraft that was moving across. So it's actually, I think we kind of assume, like ordinarily, like the military would surely not make that mistake, but certainly in that case of the Chile UFO, it definitely was a mistake, and that check, for whatever reason, wasn't made. And I think this is an important lesson that humans are fallible. I think we tend to assume that these pilots are like perfect observers. And I'm sure they're excellent observers, they're well-trained observers, but nobody's perfect. And they fly a lot of hours. So if you fly thousands of hours of aircraft time, and you have a false positive rate of, say, 1 in every 10,000 hours, which is a huge amount. Every 1 in 10,000 hours you make a mistake. You misidentify something erroneously as a UAP. That would lead to about 500 UAP reports every year. And that's about what we see, actually. So there's about 500 filed reports in like Project Blue Book and the NASA UAP Task Force. That's about how many are being reported. And then of those, most of them, as I said, like 95% have explanations which can be done after the fact. And then there's some small residual which defy easy explanation. But I think it is perfectly consistent with pilots having a finite false positive rate. And we talked about this earlier on with doing SETI. You have to know your false positive rate in order to do an experiment. Now, the problem is if I'm going to do an experiment with pilots, I don't know their false positive rate. But it could plausibly be 1 in 10,000. It could be 1 in 100,000. It could be 1 in 10. I don't know. We would have to characterize it. We would have to basically put them somehow in a simulation that they thought was totally indistinguishable from reality and inject sometimes UFOs into the simulation and see how often they caught it. That'd be their true positive rate. And then we'd have to put spurious things like balloons and other things in the background and ask how often they would erroneously conclude that was a UAP. That'd be the only way I can think of to characterize this scientifically. But without those two numbers, the false positive rate and the true positive rate, you can't do science on it. So I don't even know how science can ingest these claims if that's the only information we have. So that's kind of where we're stuck and why I support NASA's view that we need better data.
The reason that this came up for me just now was because we were talking about ranking propulsion technologies, and one of the dimensions of these videos that is so peculiar and striking, and that those who believe in UAPs are often commenting on, is that these TicTacs move in very strange ways that we do not have the technology to currently move objects ourselves. And so regardless of whether, well, for one, let's assume that they're real just for the sake of the discussion.
Well, I think the UAPs are real. Right?
Well,
because it is unidentified. It's definitely clear that there is something that's been recorded that is unidentified. That's all a UAP means, right? Doesn't mean, I think people assume if you believe UAP, that means it is alien. But that's a different question. Believing there is a UAP there is not the same thing as believing that is an alien spacecraft.
Right. So, but I'm not sure that there is, in this case, an actual UAP there, in that at least one of the other plausible alternatives is that it's just some problem with the reading, in which case there's no actual object that's being detected. It's just a problem with the equipment malfunctioning. But I'm just saying, let's assume that there is this object out there. And if there is an object out there, regardless of whether it's aliens or Chinese drones or deep secret American drones, is there any way that you know of that an object could move in the way that these objects are moving? Or maybe this is something you haven't thought of.
Yeah, I mean, the Go Fast video, I think, is a case where it seems like the object's moving at a crazy speed. That's why it's called Go Fast, I guess. But there's actually ambiguity there, because you read to truly know how fast it's moving, you have to know the altitude of that object, because it's kind of going above the water. And there's obviously like perspective effects, parallax effects as to how fast it appears to be moving. It's going to be very sensitive to whether it's close to the surface or close to the camera. So I would say the true velocity of the object is not actually measured. Similarly, like if you have a fly go across your camera, an insect go across the camera very quickly, and you assumed it was something far away, you would determine that its velocity was gigantic and it was moving at impossible speeds that no spacecraft no vehicle we know of could achieve. But in fact, it was just because you had misidentified its distance, right? Because to get the distance, you have to have stereoscopic vision. That's why we have two eyes, to measure the distance to things. Or you have to have some kind of radar sensing or something, or laser ranging to get the distance to it. So as far as I'm aware, there's no instance where that is conclusively determined that we could say for absolute certainty its velocity has been measured to be Mach 15 or whatever, like some kind of crazy speed that we wouldn't expect our vehicles to be achieving. So, but it is achievable. The point is that is a measure that we could measure that. You just need two cameras measuring the same thing at the same time at a wide enough separation that you can measure that parallax. And as far as we're, none of those Pentagon videos or any other videos have that kind of information available to us. So my suspicion is, certainly it's true. There's ambiguity about the true velocity, and my suspicion is the velocities are not what they seem. But I would love to be proven otherwise, because I think it's important as a scientist to say that. We love being surprised, and I would be fascinated to see that it truly is moving in a surprising way like that.
While the majority of this conversation I tried to keep around one theme, which is exoplanet research and aliens, there are plenty of other topics you've explored that I find really fascinating. And one that comes to mind right now, just since we mentioned AI and I mentioned Nick Bostrom in particular, is simulation theory. Yeah. And that's another big and interesting question. Yeah. Where do you weigh in on whether or not we're in a simulation and how we should even be thinking about this question?
Yeah, it's a challenging question to address because it's almost non-scientific. It's potentially non-scientific.
In that it can't be falsified?
Yeah, I think in some versions it can't be falsified. There are versions where it could be falsified. There are versions where there's glitches and things which could betray the existence of the simulation. But I guess the reason why you could always get rid of those is because presumably if anyone detected a glitch, the simulators could just reverse the tape a little bit, remove the glitch, and then resume the simulation from that previous save point, right? So there's no reason why we should expect glitches to be observable if the simulators are smart enough to stop that from happening. So it's not obvious it's truly scientific, but that doesn't mean I'm not afraid to talk about it anyway.
Great.
I try to approach things from a position of agnosticism, and certainly that's my approach with aliens, and I try to adopt the same kind of approach here. So we have kind of two possibilities, I suppose. One is that we live in a simulated universe, or let's just say that there's two possibilities. One, that simulating universes of this fidelity is even possible. It's not obvious that it's possible. And the second possibility is that this is something which is both possible and civilizations do it. Like actually people are interested in doing that activity. Now, if we live in the case, 50-50 odds between these, just to make it even, if we live in the case where it's not possible, then fine, we could be assured that that's never going to happen. If we live in the case where it is possible, then there's two possibilities within that. One, we're in the base reality. We are the simulators, or we'll become the simulators one day. Or two, that we're one of the thousands, millions, billions of simulations that presumably live beneath that. And so if this was true, this is why Elon Musk often says, it's billions of times more likely that we're simulated than not simulated. But he's implicitly assuming that this branch is even possible. So I would just say, we, as a scientist, we don't know that because we haven't seen that happen yet. Observationally, we have no evidence that this is even possible. It's not an unreasonable thing to speculate that it could be possible, but that's speculation. So if you have 50-50 odds of these two possibilities, you have one base reality here, you have one base reality here, and then you have this plethora of sub-realities. And when you equal that up into the odds, there's actually a slightly greater than 50% chance that you'd be in base reality. So I wrote a short paper about that, just kind of adding up those probabilities. But if we ever got to a point where we developed the technology, then you would change your odds immediately, and then you'd agree with Musk's 1,000,000,000 to 1. So it's okay to update your probabilities and your beliefs. That's kind of a core tenet of Bayesian inference. Is that you don't just like stick to your guns, whatever. And scientists, that's a core tenet. We don't just have dogma. We update our beliefs as new evidence arrives. So if we do develop this technology, as we're chinking our champagne glasses about our genius, we'll also have to commiserate the fact we're almost certainly simulated at that point.
Last rapid fire question, because this one I just couldn't resist because I'd never heard about it before, is what is quantum immortality?
Yeah, that was a fun one. That was actually my most recent videos. This is a thought experiment that Max Tegmark popularized, but many others had spoken about before. Max Tegmark, a famous physicist and cosmologist. And it's kind of built on the many worlds interpretation of quantum mechanics. So I should be clear about that this is an interpretation. We don't know it to be true, but it is probably the most popular interpretation of quantum mechanics amongst colleagues I at least interact with. And the idea is that every time there is a quantum decision or event that happens in the universe, whether an atom decays or doesn't decay. It's not that one event happens and the other does not happen with some probability. Both of those things really do happen, and the universe kind of branches into two sub-realities at that point. And so, of course, given the age of the universe, there would have been trillions and trillions of these branches by now, and there'd be almost potentially an infinite landscape of these many worlds living side by side, but not interacting with each other. And so, in the quantum immortality experiment, it is suggested that you could, put a gun to your head that is triggered by some kind of quantum event, like an atom decaying, and then the universe would split into two. In one of them, you'd be shot dead, and the other one, you'd survive, based off that 50-50 possibility. But the one where you're dead, as long as the death event happens almost immediately, you couldn't perceive it. You can't perceive being dead because it's an absence of experience. You can only experience being alive. So you wouldn't actually notice, your stream of consciousness would continue uninterrupted, and you would survive this Russian roulette experiment. And you could do this over and over and over and over again. And after like about a dozen times of doing this, the probability of you surviving would be, infinitesimally small. And yet you were still there. And so that would essentially prove that this many worlds interpretation was correct, because otherwise how could it possibly be that you'd survive? And so quantum immortality started with this, gun experiment, this Russian roulette experiment, but then you could, others, like I think it was Peter Lewis, extended this and argued that, all forms of death are ultimately not that different from the gun experiment. If you get hit by a car, or even if you die of old age, it's all a series of quantum steps that are happening. Everything is ultimately driven deep down by quantum events. And so surely your consciousness should continue uninterrupted in all of these realities. And so if this is true, all of us would live forever. All of our friends would die, our family would die. We'd be the only one that lived forever. But it might not be very pleasant, because even though you can't die, you would potentially be easily injured or degrade your mental capabilities, things like this. So you could become, almost like it could almost be quite torturous, in fact, as an existence. So it's an interesting experiment. I think our immediate reaction is, this seems ridiculous. Like, how could it be that we could live forever? It's not falsifiable. You can't say, well, how come there's no one around me who's 1 billion years old then? Because you would never share that reality with them. Only the person who inhabits that body actually gets to experience this continuous stream of consciousness. So it's not falsifiable. But it seems very unintuitive and uncomfortable. And I think it's a really good case of there being a conflict between two theories. One, the theory of selfhood and the theory of the mind, like what it means to have a stream of consciousness. What am I even talking about when I say consciousness and selfhood? What does that really mean? It's like difficult to pin down. And then secondly, this theory of quantum many worlds. Those two are coming together, and they are colliding and producing this very strange suggestion. And it leads most thinkers to think that something is wrong with one of these two ideas. So it's a great thought experiment to try and put pressure on our understanding. That's the best thought experiments are the ones that force us to revisit the assumptions, because in isolation, they both seem perfectly reasonable. But then when you merge them, you realize something must be amiss here.
Well, David, I fear that I have kept you a bit too long, so I'm just going to be brief here. And I'm going to say you are an incredibly knowledgeable, careful, and charismatic speaker, and it's been a real pleasure having you on the show.
Thank you so much. It's a real pleasure. Thank you for having me.